Time does not flow, it never has. And the physicists who proved it have spent the last 60 years quietly avoiding the implications. You age, stars burn out, entropy climbs. Every instinct you have, every memory, every expectation about tomorrow depends on the belief that time is real, that it moves, that the universe ticks forward from one moment to the next like a cosmic clock. This is not a philosophical opinion. This is what reality feels like. And according to the equations that govern our universe at its deepest level, it is completely, utterly wrong. In 1967, John Wheeler and Bryce-DeWitt wrote down an equation that was supposed to unify quantum mechanics with gravity. It was meant to describe the wave function of the entire cosmos. When they finished, they noticed something disturbing. Time was not in it. Not hidden, not implicit, not buried in some clever variable, just gone. The Wheeler-DeWitt equation describes a universe that does not evolve, does not change, does not move through time, because from the perspective of quantum cosmology, there is no time to move through. Einstein already hinted at this. His block universe treats past, present, and future as a single frozen sculpture, a four-dimensional object where everything that has ever happened or ever will happen simply exists, all at once, forever. Quantum eraser experiments suggest the future can rewrite the past. At the event horizon of Sagittarius A star, the 4 million solar mass black hole in the center of our galaxy, time does not slow down. It stops. And inside your own brain, neuroscience has shown that the moment you call now happened 500 milliseconds ago. You are not moving through time, you are a pattern in something that does not move. And what that means is the subject of this video. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. You check the time when you wake up. You check it before meetings, before meals, before you leave the house. You feel time passing when you're bored, slipping away when you're happy, dragging when you're waiting for something important. Time is the framework inside which your entire life happens. Every memory you have is filed under a timestamp. Every plan you make assumes a future that hasn't arrived yet. Every regret you carry lives in a past you can no longer touch. Time is so fundamental to human experience that questioning its reality feels like questioning whether the ground beneath your feet is solid or whether the air you breathe is actually there. And yet there is a group of physicists, some of the most brilliant minds working in fundamental physics today, who will tell you in private conversations, in technical papers dense with mathematics, and occasionally in public talks delivered to rooms full of uncomfortable colleagues, that time does not exist. Not in the way you think it does, not as a river flowing from past to future, not as something that moves or passes or carries you forward. According to their equations, according to the most successful frameworks we have for describing reality at its deepest level, time is not a feature of the universe. It is a feature of your perception. It is something your brain constructs, moment by moment, to make sense of a reality that at its foundation contains no such thing. This is not a fringe idea. This is not mysticism dressed up in lab coats. This is coming from the same tradition that gave you relativity, quantum mechanics, and the standard model of particle physics. These are people who have spent their lives doing the hardest math humanity knows how to do, and their equations keep telling them the same unsettling story. When you write down the laws that govern the universe as a whole, when you try to describe reality at the scale of the cosmos itself, the variable for time disappears. It is not small. It is not approximated. It is gone. The equation that describes the quantum state of the entire universe contains no variable for time. Let that sit for a second. The most fundamental equation we have for describing everything, everywhere, all at once, does not include time. It is like writing the rules of a board game and forgetting to mention that players take turns, except in this case, forgetting is the wrong word. The equation works. It makes predictions. It is mathematically consistent. Time is not missing because someone made a mistake. Time is missing because, at that level of description, it does not belong. Most physicists do not talk about this openly, not because they disagree, not because the math is wrong, but because the implications are so destabilizing that bringing them up in casual conversation feels almost irresponsible. If time does not exist, then causality, the idea that one event leads to another, that causes produce effects, becomes vastly more complicated. If time does not exist, then free will, already on shaky ground, collapses into something even harder to defend. If time does not exist, then the entire structure of human meaning, the idea that your choices matter because they shape a future that has not yet been written, falls apart. You are left standing in a universe where everything that will ever happen has already happened, where your past and your future are equally real, equally fixed, equally beyond your control. That is not the kind of thing you bring up at a faculty mixer. The silence is not conspiracy, it is caution. It is the recognition that some ideas once spoken aloud cannot be unspoken, and this one rewrites everything. Humans have always had a complicated relationship with time. We invented clocks to measure it, calendars to organize it, entire religions to explain what happens when it runs out. But even before we had tools to track it, time was the one thing everyone agreed on. The sun rises, the sun sets. You are born, you grow old, you die. Seasons cycle, rivers flow downstream, eggs break. They do not unbreak. Time moves forward, always forward, and nothing in everyday experience has ever suggested otherwise. Except some people did suggest otherwise. 2,500 years ago, a Greek philosopher named Parmenides stood in front of his students and told them that change is an illusion, that the universe is a single unchanging whole, that what we perceive as motion and transformation is a trick played by our senses. His argument was not emotional, it was logical. Change requires something to become what it was not. But if something is not, then it does not exist. And if it does not exist, it cannot become anything. Therefore, change is impossible. Therefore, time, which is just the measurement of change, is also impossible. Reality, he argued, is eternal and motionless. We just cannot see it clearly. His contemporary Heraclitus took the opposite view. Everything is change, he said. You cannot step into the same river twice, because the river is always moving. The water you touched a moment ago is already downstream. You yourself are not the same person you were a moment ago. Every cell in your body is in flux. Time is not an illusion. Time is the only thing that is real. Permanence is the illusion. Both men were trying to solve the same puzzle. How do you reconcile the feeling that reality is stable with the undeniable fact that everything in it is constantly shifting? And neither of them had instruments sensitive enough to measure what was actually happening at the smallest scales. They were working from intuition, from logic, from the limits of what human perception could tell them about the world. Modern physics has better tools, and the answer it has been quietly assembling over the past century does not settle the debate between Parmenides and Heraclitus. It makes the debate irrelevant, because the answer modern physics gives is that the question itself was wrong. Time is not an illusion, and it is not the only real thing. Time is a framework we use to describe certain kinds of processes. And at the most fundamental level, the universe does not need that framework. This started to become clear with Albert Einstein, though Einstein himself did not put it in those terms. What Einstein did was show that time is not universal, that there is no single clock ticking away in the background of reality, marking out the same seconds for everyone everywhere. Time, in relativity, is local. It depends on where you are and how fast you are moving and how deep you are in a gravitational field. Two people can disagree about how much time has passed between two events. They can disagree about whether those events happened at the same time or in sequence, and both of them can be right. That was strange enough. But relativity also suggested something deeper. It suggested that the universe is not a three-dimensional stage on which events unfold over time. It suggested that the universe is a four-dimensional object, a structure in which time is just another direction, like up or forward. In this picture, your entire life, from birth to death, exists as a single shape stretched across space-time. You are not moving through time. You are a static object embedded in it. Every moment you have ever experienced or ever will experience is already there, laid out like a film strip, equally real, equally present. Einstein himself seemed to understand the implication. In a letter written to comfort the family of a recently deceased friend, he wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. Not the kind of thing you expect to hear from a physicist. Not the kind of thing you say unless you have looked hard at your own equations and realized what they are telling you. But relativity was just the beginning. Relativity changed our understanding of time, but it did not erase it. Time was still there in the equations. It was flexible, it was relative, but it was still a variable you could point to. The real blow came later, when physicists tried to combine relativity with quantum mechanics and describe the universe as a whole. That effort produced an equation now known as the Wheeler-DeWitt equation, named after physicists John Wheeler and Bryce DeWitt. And that equation does something almost unthinkable. It removes time entirely. In classical physics, if you want to describe how a system evolves, you write down an equation that tells you how the system changes over time. You plug in the current state, you run the equation forward, and you get the future state. Time is the independent variable. It is the thing everything else depends on. But the Wheeler-DeWitt equation does not work that way. It describes the quantum state of the entire universe, and that state does not evolve, it just is. There is no time variable, there is no change, there is only a static mathematical object that encodes all possible configurations of everything that exists. Some physicists call this the problem of time, others call it the timelessness of quantum cosmology. Either way, the result is the same. If you take the most successful theories we have, relativity and quantum mechanics, and you try to apply them to the universe itself, time vanishes. Not because the math is broken, because the math is telling you something uncomfortable. This is where the silence starts to make sense. If you are a physicist who has spent years working on quantum gravity or cosmology, you know about the Wheeler-DeWitt equation. You know that time does not appear in it. You know that this is not an oversight. And you also know that if you walk into a public lecture hall and tell a room full of people that time does not exist, you will spend the rest of the evening fielding questions about whether that means their choices do not matter, whether the future is predetermined, whether we are all just puppets acting out a script that has already been written. And the honest answer to most of those questions is that we do not know. We have the math, we do not have the philosophy yet, so most physicists do not bring it up. They work on the equations, they publish their papers, they talk to each other in the careful language of technical journals, and they leave the broader implications unspoken, not because the implications are unimportant, because they are too important. Because once you start pulling on that thread, the entire fabric of everyday life starts to come apart. But the thread is already loose. The question is not whether time exists in the way we think it does. The question is what we do with the answer once we admit that it does not. Think about what it means if the past and the future are equally real. If your childhood and your death both exist right now, frozen in space-time like two frames of a film sitting side by side, every mistake you have ever made is still happening. Every moment of joy, every moment of pain, every conversation, every breath, all of it is still there, unchanging, permanent. You are not leaving your past behind. You are not moving toward your future. You are a four-dimensional shape, and the part of that shape you call now is just the part your consciousness happens to be experiencing at this instant. That is the block universe. That is what Einstein's equations suggest. That is what the Wheeler-DeWitt equation seems to confirm. And if it is true, then the feeling you have right now, the feeling that you are living through a single moment that is somehow special, somehow more real than the moments that came before or the moments yet to come, that feeling is an artifact of how your brain processes information. It is not a property of the universe. It is a property of you. Your brain is a machine that turns physical processes into the experience of time. It takes sensory input. It orders that input into a sequence. It creates the sensation of duration and flow and change. But the universe itself does not flow. The universe is a static structure. What you perceive as time passing is really just your awareness sliding along a path through that structure, like a bead moving along a wire. The wire is not moving. You are not moving through space-time. You are space-time. And the sense that time is passing is something your nervous system is manufacturing for you, moment by moment, because that is the only way a biological organism can navigate a universe that at its foundation does not change. None of this is fringe. None of this is speculative in the way that multiverse theories or simulation hypotheses are speculative. This is coming directly from the core of modern physics. Relativity is the most well-tested theory in the history of science. Quantum mechanics is the foundation of every piece of technology you used today. When you combine them, when you ask what they say about time, the answer they give is that time is not fundamental. It is emergent. It is something that appears at large scales, in certain contexts, under certain conditions, but it is not baked into the deep structure of reality. So why do physicists stay silent? Because once you say that out loud, once you admit that the equations are pointing toward a timeless universe, you open the door to a set of questions that science is not equipped to answer. If time does not exist, does causality exist? If causality does not exist, how do we make sense of the fact that striking a match causes it to light? How do we explain that kicking a ball causes it to move? The equations work. The predictions match observations, but the interpretation, the story we tell ourselves about what the equations mean, that story has to be rebuilt from the ground up. And then there is free will. If your entire life already exists as a static structure in space-time, if the choices you will make tomorrow are already there, already real, already fixed, then in what sense are you making a choice? You feel like you are deciding. You feel like the future is open. But if the block universe is real, then the future is not open. It is already written. You are reading it, not writing it. Some physicists argue that this does not eliminate free will. They say that free will was never about the future being undetermined. It was about your actions being the result of your own internal processes rather than external coercion. In that sense, you are still free even in a block universe. Your decisions are still yours. They were always going to be yours. The fact that they are already embedded in space-time does not change that. Other physicists are less optimistic. They will tell you quietly over drinks late at night that the block universe is exactly as terrifying as it sounds, that it does mean your choices were never really choices, that it does mean everything you will ever do has already happened, that the feeling of agency you carry around, the sense that you are steering your life in real time, is a story your brain tells you to make sense of a reality that does not actually contain steering or real time. This is not an argument most people want to have. Not at conferences, not in classrooms, not at dinner parties. So the silence persists. The equations sit in the journals, the implications sit unspoken, and the rest of the world goes on checking the time, planning the future, remembering the past, certain that time is real because they can feel it passing. But the equations do not care what you feel, and they keep saying the same thing. Einstein did not set out to kill time. He set out to solve a problem with light. Specifically, why light always travels at the same speed no matter how fast you are moving when you measure it. That fact, confirmed by experiment after experiment in the late 1800s, made no sense under the rules of physics as they existed at the time. If you are standing still and you measure the speed of a passing car, you get one number. If you are driving toward that car, you measure a higher speed. If you are driving away from it, you measure a lower speed. Velocities add. That is how motion works. Except light does not behave that way. Fire a beam of light across a room and measure its speed. You get 299,792,458 meters per second. Now get on a spaceship, accelerate to half the speed of light, and measure that same beam as it passes you. You still get 299,792,458 meters per second, not faster, not slower, exactly the same. It is like running toward a train and discovering that no matter how fast you run, the train always approaches you at the same speed. It should not work, but it does. Every experiment ever performed confirms it. Light always travels at the same speed relative to whoever is measuring it. Einstein looked at that fact and realized something had to give. If the speed of light is constant, and if speed is distance divided by time, then either distance or time or both must be flexible. There is no other way to make the math work. So he made a choice. He said, fine, they are flexible. Space can stretch, time can slow down. The universe will bend itself into whatever shape it needs to be in order to keep the speed of light constant. That choice, published in 1905 in a paper called On the Electrodynamics of Moving Bodies, became special relativity, and it rewrote the rules. The core idea is simple to state and almost impossible to accept emotionally. There is no universal clock, no single timeline ticking away in the background of the universe that everyone agrees on. Time is local. It depends on your motion. Two observers moving at different speeds will measure time passing at different rates, not because their clocks are broken, because time itself, whatever that word refers to, is different for each of them. Put one observer on a spaceship traveling at 90% the speed of light and leave the other one on Earth. Let the spaceship travel for what feels like 1 year to the person on board. When they return to Earth, 10 years will have passed for the person who stayed behind. Not because anyone made a mistake, because that is what time does when you move that fast. It slows down. Not metaphorically, literally. The person on the spaceship aged 1 year. The person on Earth aged 10. Both experienced time normally from their own perspective. But when they compare notes, the universe itself has disagreed about how much time passed. This is not speculation. This has been measured. Atomic clocks flown on airplanes tick at different rates than atomic clocks left on the ground. Satellites in orbit have to account for the fact that time runs slightly faster up there than it does down here. GPS would not work if the system did not correct for relativistic time dilation. Your phone is compensating for Einstein's equations every time you ask it for directions. The effect is real. Time is not a fixed background. It is something that bends. Special relativity deals with objects moving at constant speeds. General relativity, published in 1915, extended the idea to include gravity. Einstein showed that gravity is not a force in the way Newton thought it was. Gravity is the curvature of space-time itself. Mass bends the fabric of space and time around it. The more massive an object is, the more it warps space-time. And the deeper you are in that warp, the slower time runs. Sit on the surface of a planet, and time moves slightly slower than it does in empty space far from any mass. Sit near the surface of a black hole, and time slows to a crawl. To an outside observer, you would appear to freeze. Your clock would tick so slowly that it might take 1,000 years of their time for 1 second to pass on your watch. From your perspective, nothing would feel different. You would experience time normally, but the universe would be aging around you at a furious rate. By the time your watch ticked forward 1 minute, civilizations could have risen and fallen in the universe outside. That is what general relativity says, and every test we have ever devised has confirmed it. Time is not uniform. It is not the same everywhere. It depends on where you are, and how fast you are moving, and how deep you are in a gravitational well. Two people standing at different altitudes on a mountain will age at slightly different rates. The difference is tiny, but it is real, and if you could measure with enough precision, you could detect it. All of that is strange, but it gets stranger. Because once you accept that time is flexible, once you accept that there is no universal now, the next logical step is to ask what that means for the structure of reality itself. And the answer, the one that falls out of the math when you work through it carefully, is that the universe is not a three-dimensional space that changes over time. The universe is a four-dimensional object. A single unified structure in which time is just another dimension, like width or height or depth. Past, present, and future are not separate. They are all part of the same thing, and that thing does not change, it simply exists. Physicists call this the block universe. The name is deliberate. It is meant to evoke exactly the image it sounds like: a solid block, a frozen object, a four-dimensional sculpture in which every event that has ever happened or ever will happen is already carved into place. Your birth is in there, your death is in there, every word you have ever spoken, every thought you have ever had, every choice you will make tomorrow, all of it exists simultaneously, laid out across space-time like cities on a map. You are not moving through time, you are a shape embedded in it. A long, thin, spaghetti-like structure stretching from the moment you were born to the moment you die, and every point along that structure, every moment of your life, is equally real. This is not a metaphor. This is the picture that emerges when you take Einstein's equations seriously. Stanford University hosts an online FAQ about general relativity, originally created to support NASA's Gravity Probe B mission. One of the entries addresses this directly. It says that in the four-dimensional space-time picture, the universe does not evolve, it simply exists. World lines, the paths that objects trace through space-time, do not move. They are static curves, frozen in place. The FAQ describes a particle's entire history as a spaghetti-like line that stretches from the past to the future. That line does not grow or change. It is already complete. All of it is there at once. Think about what that means. If the block universe is real, then right now, at this moment, every future event is already sitting in space-time waiting for you to experience it. not in a probabilistic sense, not as a range of possibilities that will collapse into reality when you get there, but as fixed, definite events that are just as real as the chair you are sitting in. The conversation you will have tomorrow morning already exists. The meal you will eat next week already exists. The last breath you will ever take already exists. You have not experienced those things yet. But that is a fact about your consciousness, not a fact about the universe. The universe contains all of those moments right now. You just have not gotten to them yet. This is where the block universe starts to feel less like a physics idea and more like a trap. Because if the future already exists, if it is already out there in space-time as real and as solid as the past, then in what sense is it the future? The word future implies something that has not happened yet, something that is not yet real. But in the block universe, the future is real. It has the same ontological status as yesterday. The only difference is that your consciousness has not reached it yet. You are like someone reading a book. The later chapters exist. They are already written. You just have not turned the page. The analogy that gets used most often is a movie reel. Imagine a film strip stretched out on a table in front of you. Every frame is there, the beginning, the middle, the end. All of it exists simultaneously. When you watch the movie, you experience it one frame at a time. The projector moves through the strip, lighting up each image in sequence, creating the illusion of motion and change. But the strip itself is not moving. The frames are not appearing one by one. They are all there, laid out in front of you, static and complete. Your experience of the movie as something that unfolds over time is an artifact of how the projector works. The movie itself does not unfold, it just is. The block universe says that reality is like that film strip. All of space-time, from the Big Bang to the heat death of the universe, is a single object, a four-dimensional block in which every event is a frame. And what you experience as the passage of time is just your consciousness moving through that block, experiencing one slice at a time. You feel like you are living through a moment that is uniquely real, uniquely present, but that feeling is a trick. The moment you experienced an hour ago is still there. It has not gone anywhere. The moment you will experience an hour from now is already there. It is not coming toward you. You are moving toward it. Except moving is the wrong word because motion implies change, and the block universe does not change. You are not moving through space-time, you are space-time. And the sensation of time passing is something your brain is constructing for you because that is the only way a biological organism embedded in a four-dimensional block can make sense of its own existence. Einstein himself seemed to understand the implications. In 1955, just weeks before his own death, he wrote a letter to the family of his lifelong friend Michel Besso, who had recently passed away. The letter is famous now, quoted in almost every popular discussion of relativity and time. Einstein wrote that Besso had departed from this strange world a little ahead of him, but that this meant nothing. He wrote that for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion, not a comforting illusion, not a useful illusion, a stubborn one, the kind you cannot get rid of even when you know better. That line is doing a lot of work. Einstein is not saying that time does not feel real. He is saying that the feeling is misleading. That the equations, his equations, point to a universe in which past, present, and future are all equally real, all equally existent, all part of a single frozen structure. And the sense you have that only the present is real, that the past is gone and the future has not arrived yet, that sense is something your mind imposes on the data. It is not something the universe actually contains. This is the first major pillar supporting the claim that time does not exist. Relativity does not directly say that time is an illusion. What it says is that time is relative, that there is no universal now, that observers moving at different speeds or sitting at different depths in a gravitational field will disagree about when events happen and in what order. And once you accept that, once you admit that there is no privileged moment that counts as the present for the entire universe, the concept of a present moment starts to fall apart. If there is no universal now, then what does it mean to say that something is happening now? Now for whom? Now in which reference frame? The block universe is one answer to that question. It says that the present moment is not a feature of the universe, it is a feature of your perspective. The universe does not have a present, it has a structure, and your experience of moving through that structure, one moment at a time, is a local phenomenon, a side effect of being a conscious observer embedded in space-time, not a fundamental property of reality. National Geographic, summarizing Einstein's legacy, emphasizes that one of the key insights of relativity is that there is no universal clock, no single reference frame that everyone agrees on. Space. Combe puts it more bluntly, saying that events that occur at the same time for one observer could occur at different times for another. The Department of Energy's explainer on spacetime adds a critical detail. It notes that while distant observers may disagree on the order of events, they will always agree on causal order for events connected by signals slower than light. That caveat matters because it means the block universe is not total chaos. There is still structure. Causes still precede effects in every reference frame. What changes is the notion of simultaneity. Two events that happen at the same time for you might happen in sequence for someone else, and both of you are right. The universe does not pick sides. This leads to a natural question. If the block universe is real, if your entire life is already out there in space-time like a sculpture frozen in 4 dimensions, then is the future predetermined? Is every choice you will ever make already decided? The short answer is that relativity does not directly answer that question. Relativity tells you about the structure of spacetime. It does not tell you whether the events in spacetime were inevitable or whether they could have been different. That is a separate question. A question about determinism, not about the geometry of the universe, but the block universe strongly suggests an answer. If the future already exists, if it is sitting out there in space-time right now as solid and as definite as the past, then it is hard to see how it could be any different than it is. The sculpture is already carved, the movie is already filmed. You have not watched it yet, but that does not mean the ending is up for grabs. The ending is already there. You are going to experience it. And when you do, it will feel like you are making choices, like you are steering your life in real time. But the block universe says that those choices were always part of the sculpture. They were always going to happen the way they happened, not because something forced them to happen that way, just because that is the shape space-time has. That is what the 4-dimensional object we call the universe looks like when you zoom out far enough to see the whole thing. Some physicists are comfortable with that conclusion, others find it deeply troubling. The debate is not about the math. The math is clear. Relativity works. Its predictions have been confirmed over and over again in every experiment we have ever designed to test it. The debate is about what the math means, about whether the block universe is the right way to interpret relativity or whether there is some other way to make sense of a universe in which time is relative but the future is still open. One thing the block universe does not tell you is why you experience time the way you do. It does not explain why you remember the past but not the future. It does not explain why causes seem to precede effects in your experience, even though, in the block universe, causes and effects are just 2 regions of spacetime sitting next to each other with no inherent direction. It does not explain why you feel like you are moving forward through time rather than backward or sideways or not at all. The block universe is a picture of what reality looks like from the outside, from a God's eye view in which all of space-time is visible at once. But you do not have that view. You are inside the block, and from inside, time feels real. It feels like it flows. It feels like the present is special and the future is uncertain. The block universe says that feeling is an illusion, but it does not explain where the illusion comes from. That is a harder problem, and it is one that physics alone cannot solve. What relativity does give you is the structure, the framework, the geometric picture of a universe in which space and time are woven together into a single fabric, and that fabric does not evolve, it simply exists. Every point in space-time is as real as every other point. Past, present, and future are all part of the same object. The Big Bang is not an event that happened long ago. It is a region of space-time. The heat death of the universe is not an event that will happen in the distant future. It is another region of space-time. Both regions exist right now, in the sense that both are part of the four-dimensional structure. You cannot visit the Big Bang because it is not in your past light cone. You cannot visit the heat death because it is not in your future light cone. But both are real. Both are there. And the fact that your consciousness happens to be localized to a particular slice of space-time does not make that slice more real than the others. It just makes it the slice you are currently experiencing. This is not easy to visualize. Human brains did not evolve to think in 4 dimensions. We are built to navigate 3-dimensional space and to experience time as something that flows. The block universe asks you to let go of that intuition, to imagine a reality in which nothing flows, in which all moments exist simultaneously, in which your entire life is a static shape, and the feeling that you are living through it, moment by moment, is a feature of your nervous system, not a feature of the universe. If you find that picture disturbing, you are not alone. A lot of physicists find it disturbing, not because it is wrong. The math is too solid for that. But because it forces you to confront the possibility that the most basic feature of your experience, the sense that time is passing, is not a property of reality. It is a story your brain tells you. A necessary story maybe, a useful story, but not a true one. And if the block universe is just the first piece of the puzzle, if relativity is just the opening argument, then the case against time is about to get significantly stronger, because relativity still leaves time in the equations. It makes time flexible, it makes time relative, but it does not erase it. The real trouble starts when you try to combine relativity with quantum mechanics and describe the entire universe at once. That is where time does not just bend, that is where time disappears completely. That is the Wheeler-DeWitt equation, and that is where the silence among physicists gets loudest. So relativity bent time. It made time flexible, relative, observer-dependent. It turned the universe into a 4-dimensional block where past, present, and future all sit frozen together like a sculpture carved from space-time itself. That was disturbing enough, but relativity still left time in the equations. It was a variable you could point to. It was something you could measure, even if different observers measured it differently. Time was strange under Einstein, but it was still there. Then physicists tried to combine relativity with quantum mechanics, and that is when time did not just bend, that is when time vanished completely. The problem started innocently enough. Both theories work. Relativity describes gravity, the motion of planets, the bending of light around massive objects, the expansion of the universe. Quantum mechanics describes atoms, particles, the behavior of light and matter at the smallest scales. Both theories make predictions that match experiments to absurd levels of precision. Relativity has been tested with atomic clocks on airplanes, with GPS satellites, with gravitational wave detectors picking up ripples in space-time from colliding black holes billions of light years away. Quantum mechanics is the foundation of every piece of electronics you own. Your phone, your computer, the LED lights in your room. None of it works without quantum mechanics. Both theories are spectacularly successful, and they cannot stand each other. The core issue is that they treat time in fundamentally incompatible ways. In quantum mechanics, time is a background parameter. It is the stage on which events unfold. You describe how a quantum system evolves by writing down an equation that tells you how the system's wave function changes over time. Time is external. It is not part of the system. It is the thing against which you measure the system's behavior. You plug in a time, you get a state. Plug in a different time, you get a different state. Time is the independent variable, and everything else depends on it. In general relativity, time does not work that way. Time is not a background. Time is part of the structure you are trying to describe. Space-time is dynamical. It curves. It warps. It responds to the presence of mass and energy. You cannot treat time as a fixed external parameter because time itself is one of the things your equations are solving for. Asking what the universe looks like at a particular time is like asking what a river looks like from the perspective of the water. The question does not quite make sense because the water is part of the thing you are trying to describe. For decades, physicists tried to paper over this mismatch. They worked in regimes where one theory or the other dominated. If you are describing planets orbiting stars, you use relativity and you ignore quantum mechanics. If you are describing electrons in an atom, you use quantum mechanics and you ignore the curvature of spacetime. That approach works fine for almost every situation anyone has ever encountered, but it breaks down when you try to describe the universe as a whole, or when you try to describe what happens near the center of a black hole, or when you try to describe the first moments after the Big Bang. In those situations, you cannot ignore either theory. Gravity is too strong to leave out relativity. The scales are too small to leave out quantum mechanics. You need both, and nobody knows how to make both work at the same time. One of the earliest and most ambitious attempts to solve this problem came in 1967. That year, two physicists, John Wheeler and Bryce-DeWitt, independently developed an equation designed to describe the quantum state of the entire universe. Not a piece of the universe, not a subsystem, the whole thing, every particle, every field, every bit of space-time, all at once. The equation they wrote down is now called the Wheeler-DeWitt equation. And it does something so strange that physicists are still arguing about what it means more than 50 years later. It removes time, not in a subtle way, not as an approximation. The Wheeler-DeWitt equation, in its standard form, contains no time variable at all. There is no letter t sitting in the equation waiting for you to plug in a value. There is no parameter that tells you how the universe evolves from one moment to the next. The equation describes a quantum state, and that state does not change, it does not evolve, it just is. If that sounds like a mistake, it is not. It is a direct consequence of trying to apply the rules of quantum mechanics to a universe where spacetime itself is part of what you are trying to describe. In ordinary quantum mechanics, you have a wave function that tells you the probability of finding a system in a particular configuration. That wave function evolves over time according to an equation called the Schrödinger equation. The Schrödinger equation is explicitly time-dependent. It tells you how the wave function at time t relates to the wave function at time t plus 1 second. But the Schrödinger equation only works if you have an external clock, something outside the system that you can use to measure time. When the system you are describing is the entire universe, there is no outside, there is no external clock. There is nothing outside the universe ticking away in the background. Time, if it exists, is inside the system. And once time is inside the system, once it is part of what you are trying to describe, rather than the thing you are describing it against, the usual rules stop working. Wheeler and DeWitt were trying to write down a quantum version of Einstein's equations for gravity. They started with the same framework Einstein used, a description of spacetime as a dynamical object that curves in response to matter and energy. Then they tried to apply quantum rules to that description. What they got was an equation that describes the wave function of the universe, but unlike every other wave function in quantum mechanics, this one does not evolve in time. It satisfies a constraint. The constraint says that the total energy of the universe, including the energy associated with the geometry of spacetime itself, must equal zero. And once you impose that constraint, time drops out. Think about what that means. In the most complete quantum description we know how to write down, the universe does not have a history. It does not evolve. It does not change. It is a single static mathematical object. Every configuration that the universe could possibly be in, every possible arrangement of particles and fields and spacetime curvature is encoded in that object, and the equation tells you which configurations are allowed and which are not. But it does not tell you how to get from one configuration to another, because there is no such thing as getting from one configuration to another. There is no sequence. There is no before and after. There is just the wave function sitting there, timeless. This is called the problem of time in quantum gravity, not because anyone is confused about what clocks measure, but because when you try to write down the most fundamental equation describing reality, the thing that is supposed to explain everything, time is not in it. The equation works. It is mathematically consistent. Physicists have spent decades studying it, extending it, trying to extract predictions from it, but the equation itself does not contain time, and nobody knows what to do with that. The easiest way to understand why this happens is to think about what it means to describe the universe as a whole. When you describe a subsystem, a planet, a particle, a person, you can always step outside that system and watch it from a distance. You can use a clock that is not part of the system to measure how the system changes, but the universe has no outside. There is no external vantage point. There is no clock sitting outside the universe ticking away while the universe evolves. If time is going to mean anything in a quantum description of the universe, it has to be constructed from things inside the universe. It has to be relational. One part of the universe has to serve as a clock for the rest. And the Wheeler-DeWitt equation is telling you that when you do the math carefully, when you take the constraints seriously, there is no preferred way to split the universe into a clock and everything else. The split is arbitrary, and any description that depends on that split is incomplete. What you are left with is a picture of the universe as a single timeless object. Physicists sometimes call this the frozen universe, not frozen in the sense that nothing moves, frozen in the sense that the most complete description, the God's eye view, does not contain motion or change. It contains a static structure, and what we perceive as time, what we experience as the flow of moments, one after another, is something that emerges when you look at correlations between different parts of that structure. It is not fundamental, it is derived. It is something that appears when you zoom in, when you pick a subsystem to act as a clock and describe everything else relative to that clock. But the universe itself, in its most complete quantum description, does not tick. It does not evolve. It simply is. Some physicists have tried to make peace with this. They argue that the Wheeler-DeWitt equation is not saying time does not exist. It is saying that time is emergent. That time is not a fundamental ingredient of reality, but something that appears at larger scales, in certain contexts, when you are not looking at the universe all at once. Carlo Rovelli, one of the founders of a theory called loop quantum gravity, has written extensively about this. He argues that time is relational, that it only makes sense to talk about time when you compare one system to another. A clock ticking relative to a particle moving, a particle decaying relative to the expansion of space. But there is no absolute time, no universal clock ticking in the background, and the Wheeler-DeWitt equation is the mathematical expression of that fact. Other physicists are less comfortable. They look at the equation and see a problem that has not been solved. They argue that removing time from the fundamental description is too high a price to pay, that something must be wrong with the formalism, that we are missing a piece of the puzzle, that once we figure out the right way to do quantum gravity, time will come back. It will turn out that the timelessness of the Wheeler-DeWitt equation was an artifact of an incomplete theory, not a feature of reality itself. The debate is not settled. It may never be settled, but the equation is there, and it has been there since 1967, and every attempt to fix it, every modification proposed to bring time back into the picture, either fails to work mathematically or reintroduces the same problems the equation was supposed to solve. The Wheeler-DeWitt equation stands, and it keeps saying the same thing. The quantum state of the universe does not evolve in time. Here is a concrete way to think about it. Imagine you want to describe the entire universe at the quantum level. You start by listing everything that could vary, the position of every particle, the strength of every field, the curvature of space-time at every point. That list is enormous, infinite really, but in principle you could write it down. Now you want to describe the quantum state of all of that. In ordinary quantum mechanics, you would write down a wave function that assigns a probability amplitude to every possible configuration. This configuration has amplitude A, that configuration has amplitude B. The square of the amplitude gives you the probability of finding the universe in that configuration if you were to measure it. So far so good. But now comes the question, how does that wave function change over time? In ordinary quantum mechanics, you would write down the Schrödinger equation and evolve the wave function forward. But to do that, you need a time variable. You need to know what time it is now, so you can figure out what the wave function will look like 1 second from now. And that is where the problem starts. Time is not external to the universe. Time is part of the geometry of space-time, and space-time is one of the things you are trying to describe with your wave function. You cannot use time as an external parameter because time is inside the system. It is one of the variables. It is part of the configuration space. What Wheeler and DeWitt realized is that if you take the constraints from general relativity seriously, if you insist that the total energy of the universe, including the energy of space-time itself, must equal zero, then the Schrödinger equation collapses into something much simpler and much stranger. It collapses into a constraint equation, an equation that does not tell you how the wave function evolves. It tells you which wave functions are allowed, and the wave functions that are allowed do not depend on time because time is not a variable in the equation. The wave function of the universe is timeless. This is not a fringe idea. This is not a speculative proposal from the fringes of physics. The Wheeler-DeWitt equation is a cornerstone of quantum cosmology. It is taught in graduate courses. It appears in textbooks. It is the starting point for almost every modern attempt to understand how quantum mechanics and gravity fit together. And it has this deeply unsettling property that time is not in it. Some researchers have tried to recover time by identifying a subsystem of the universe that can act as a clock. They call this relational time or emergent time. The idea is that even though the universe as a whole does not evolve, you can still define a notion of change by comparing one part of the universe to another. You pick something, maybe the expansion of space, maybe the oscillations of a quantum field, maybe the motion of particles, and you use that something as a clock. Then you describe how everything else changes relative to that clock. In that framework, time is not gone. It is just not fundamental. It is a relationship between subsystems. It is something that emerges when you stop looking at the universe all at once and start looking at pieces of it interacting with each other. This approach has some appeal. It lets you keep the language of time. It lets you say that things evolve, that causes precede effects, that the future is different from the past. But it comes with a cost. The cost is that the choice of clock is arbitrary. Different choices give you different notions of time. And there is no preferred choice, no clock that is more fundamental than any other. Which means time, in this picture, is not a feature of reality. It is a feature of how you choose to describe reality. It is observer-dependent, or more precisely, it is subsystem-dependent. Two observers using different subsystems as clocks will disagree about how much time has passed, and both of them will be right, just like in relativity. Except now it is worse. Because in relativity, time was still a coordinate. It was part of the geometry of spacetime. In quantum cosmology, time is not even that. It is a derived quantity, a bookkeeping device, a way of organizing correlations between parts of the universe. One of the most striking things about the Wheeler-DeWitt equation is how little attention it gets outside of specialist circles. If you talk to physicists who work on quantum gravity, they will tell you about it. They will tell you it is central. They will tell you it is one of the hardest unsolved problems in theoretical physics. But if you talk to physicists in other fields, or if you read popular accounts of modern physics, the equation barely comes up. It is mentioned in passing, if at all. And when it is mentioned, the implications are usually softened. The language shifts. Instead of saying time does not exist, people say time is emergent. Instead of saying the universe is timeless, they say the universe does not evolve in the usual sense. The message gets diluted, and the result is that most people, including most scientists, have no idea that the most fundamental equation we have for describing the universe contains no time variable. Why the silence? Part of it is that the equation is hard to explain. It involves abstract mathematics, quantum field theory, differential geometry. It is not the kind of thing you can convey in a single sentence. But part of it is that the implications are uncomfortable. If the Wheeler-DeWitt equation is right, if the universe really is timeless at the most fundamental level, then everything we experience as change, as motion, as history, is in some sense a fiction, not a lie exactly, but not a fundamental truth either. A useful approximation. A story we tell ourselves because we are embedded in the universe, and we do not have access to the God's eye view. We are subsystems. And subsystems, by their nature, can only see correlations between parts. They cannot see the whole, and the correlations we see look like time passing. But the whole, the universe itself, does not pass. It does not flow. It simply is. This is where the Wheeler-DeWitt equation connects back to the block universe. Relativity gave us the picture of a four-dimensional structure in which past, present, and future all exist simultaneously. The Wheeler-DeWitt equation gives us the quantum version of that picture. It says that the universe at the quantum level is a single static wave function, and that wave function encodes every possible history, every possible sequence of events, every possible way the universe could be. But it does not single out one sequence as the real one. It does not say this is what happened first and this is what happened next. It just assigns amplitudes to configurations, and those amplitudes do not change because there is no time for them to change in. What does that mean for causality? If time is not fundamental, if the universe does not evolve, then what does it mean to say that one event causes another? Physicists have spent decades working on that question. The answer seems to be that causality is also emergent, that it is not a fundamental feature of the Wheeler-DeWitt equation, but something that appears when you look at subsystems, when you pick a clock and describe how other things change relative to that clock. In that description, you can still say that A caused B. You can still say that events happen in sequence, but that sequence is not fundamental. It is a feature of your choice of clock. A different clock might give you a different sequence, or it might blur the distinction between cause and effect entirely. The deeper you go, the less sharp the boundaries become. Some researchers have pointed out that the Wheeler-DeWitt equation is not the only game in town. There are other approaches to quantum gravity: string theory, loop quantum gravity, causal set theory. Some of these approaches handle time differently. Some of them keep time as a fundamental ingredient. Some of them propose that time is emergent but in a different way than the Wheeler-DeWitt picture suggests. But none of them have solved the problem cleanly. And all of them have to contend with the same basic tension. Quantum mechanics wants time to be external. General relativity wants time to be internal. And nobody has figured out how to satisfy both demands at once without giving something up. What the Wheeler-DeWitt equation has given us, at a minimum, is a clear mathematical statement of the problem. It shows you exactly where the tension lives. It shows you what happens when you try to apply quantum rules to a universe where space-time is dynamical, and what happens is that time disappears. Maybe that disappearance is telling us something deep about the nature of reality. Maybe it is telling us that our formalism is incomplete. But either way, the equation is there, and it is not going away. And the more carefully you study it, the harder it becomes to argue that time, as we experience it, is a fundamental feature of the universe. This is the second pillar. Relativity gave us the block universe, the idea that past, present, and future all exist simultaneously. The Wheeler-DeWitt equation gave us the timeless wave function, the idea that the quantum state of the universe does not evolve. Together, they form a picture that is hard to ignore. Time is not fundamental. Time is something that emerges when you are not looking at the whole. When you zoom in, when you pick a subsystem, when you describe one part of the universe relative to another, time reappears. It looks real, it feels real, but the equations that describe the universe most completely do not contain it. And if that were the whole story, it would be strange enough. But it is not the whole story, because quantum mechanics has another trick up its sleeve, a trick that suggests the past is not even fixed, that events that have already happened can be changed by measurements you make now, that the arrow of time, the thing that separates cause from effect, might not be as rigid as we thought. That is the quantum eraser. That is retrocausality. And that is where things stop being merely strange and start being outright disturbing. So the Wheeler-DeWitt equation told us that the most complete description of the universe contains no time variable, that the quantum state of reality is timeless, a single frozen mathematical object encoding every possible configuration of everything that exists. That was disturbing enough. It said that time, as we experience it, is not fundamental, that it emerges when you pick a subsystem, when you zoom in, when you stop trying to describe the whole universe at once and start describing pieces of it relative to each other. Time is relational. Time is derived. Time is not baked into the deepest layer of reality. But at least the past was safe. At least what already happened stayed happened. At least the arrow of time pointed in one direction. Causes preceded effects. You could not unscramble an egg. You could not unburn a log. The future might not be open in the block universe. It might already exist out there in space-time waiting for you to experience it, but at least the past was fixed. At least yesterday was done. At least the events that had already occurred were real and solid and beyond dispute. Quantum mechanics says otherwise. Not in a vague philosophical sense, in a concrete experimental sense, in a series of experiments that have been performed in laboratories around the world, tested and retested, refined and extended, physicists have shown that the past is not as solid as it looks, that measurements you make now can influence or at least correlate with events that already happened. That information about what occurred can be erased after the fact, and when it is erased, the event itself changes character, not metaphorically, not in your memory of the event, in the physical record, in the data, in the pattern that shows up on the detector screen. The experiments are called quantum erasers, and they are some of the most unsettling pieces of evidence we have that time does not work the way your intuition insists it must. To understand what a quantum eraser does, you first need to understand the experiment it builds on, the double-slit experiment. If you have heard of quantum mechanics at all, you have probably heard of this one. It is the gateway drug. The experiment that breaks your brain just enough to make you realize that reality at small scales does not behave the way reality at human scales behaves. And once your brain is broken, once you have accepted that particles can be in two places at once and that observation changes outcomes, the quantum eraser becomes possible. Here is the setup. You take a source that fires particles, photons, electrons, it does not matter. One particle at a time. You aim that source at a barrier with two narrow slits cut into it. Behind the barrier, you place a detector screen that records where each particle lands. Then you turn on the source and start firing. If particles were simple bullets, little hard spheres flying through space, you would expect them to pass through one slit or the other and pile up in two clusters on the screen. One cluster behind the left slit, one cluster behind the right slit. Two bright bands, that is what bullets would do. That is not what particles do. What you see instead is an interference pattern. A series of alternating bright and dark bands spread across the screen. The pattern looks exactly like what you get when you send waves through two slits. Water waves, sound waves, light waves. Waves interfere with themselves. Where the peaks from both slits line up, you get a bright band. Where a peak from one slit meets a trough from the other, they cancel out and you get a dark band. The math is straightforward. The pattern is unmistakable. Particles, fired one at a time, produce a wave interference pattern. That makes no sense if particles are particles. A single particle cannot go through both slits. It has to pick one. But the pattern you see on the screen is only possible if something went through both slits and interfered with itself on the other side. Somehow, each particle is behaving like a wave spread out across space, passing through both openings simultaneously, then colliding with itself to produce the interference pattern. Quantum mechanics explains this by saying that the particle does not have a definite position until you measure it. Before measurement, the particle is in a superposition. It exists in a state that includes both paths, through the left slit and through the right slit, not one or the other, both, at the same time. The wave function, the mathematical object that describes the particle, spreads out and passes through both openings, and when the wave function hits the detector screen, it collapses. The particle suddenly has a definite position. It shows up as a single dot. But the location of that dot is influenced by the interference between the two paths. Fire enough particles, let each one collapse into a dot, and the dots pile up into the interference pattern. Bright bands where the wave function was strong, dark bands where it was weak. That is weird, but it is just the beginning. Because now someone asks the obvious question: what if we try to find out which slit the particle actually went through? What if we put a detector at each slit that records whether a particle passed through? If we can tell which path the particle took, then it cannot have taken both paths. So what happens to the interference pattern? You do the experiment, you add detectors at the slits, you fire the particles, and the interference pattern vanishes, gone. What you see instead is exactly what you would expect from bullets. Two clusters, one behind each slit. The act of measuring which slit the particle went through destroys the interference. The particle, once observed, stops behaving like a wave and starts behaving like a particle. It picks a slit, it goes through, it lands in a cluster. No interference, no alternating bands, just two piles. This is the observer effect. Not because consciousness does anything magical, but because measurement, any kind of interaction that extracts information about the system, forces the system to commit to a definite state. Before you measure, the particle is in both places. After you measure, it is in one place. And once it is in one place, it cannot interfere with itself. The wave function collapses. The superposition ends. The which path information, the knowledge of which slit the particle went through, is incompatible with interference. Physicists spent decades confirming this. The results are rock solid. If you have which path information, you do not get interference. If you do not have which path information, you do. The universe does not let you have both. You can watch the particle go through a specific slit, or you can watch it interfere with itself, but you cannot do both at once. Knowing destroys interfering. That is already strange. But now comes the quantum eraser, and this is where the past starts to look less permanent. The idea is simple. What if you measure which path the particle took, so the interference pattern disappears, and then you erase that measurement? You delete the which path information. You make it so that even though you measured which slit the particle went through, nobody can ever recover that information. Not you, not anyone, not even in principle. The information is gone, erased. Does the interference pattern come back? The answer is yes, and it is not a theoretical yes. It has been done multiple times, in multiple configurations, and every time the result is the same. If you erase the which path information, even after the particle has already hit the detector screen, the interference pattern reappears in the data. Let that sit for a second. The particle has already been detected. It has already landed. Its position has been recorded. The experiment from the particle's perspective is over, and then you erase the measurement. You destroy the which path information, and when you do that, the pattern that shows up in the data changes, not the individual dots. Those are already there. But the way the dots are distributed, if the information is available, they cluster. If the information is erased, they interfere. The past event, the moment the particle hit the screen, seems to depend on what you do later. Here is how one of the most famous versions of the experiment works. You start with a source that produces pairs of entangled photons. Entanglement is another quantum weirdness. Two particles become linked in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance and spent years trying to prove it could not be real. He was wrong. Entanglement is real. It has been tested over and over. It is one of the best confirmed predictions in all of physics. You create a pair of entangled photons. Call one the signal photon and the other the idler photon. You send the signal photon toward a double slit. It passes through, hits a detector screen, and its position is recorded. Meanwhile, the idler photon is sent down a different path, a much longer path, long enough that the signal photon has already been detected by the time the idler photon reaches its own set of detectors. Now here is the trick. You set up the idler photon's path so that you can choose, after the signal photon has already been detected, whether to measure which slit the signal photon went through or to erase that information. You do this by manipulating the idler photon. Because the two photons are entangled, measuring the idler gives you information about the signal. If you measure the idler in a way that preserves which path information, you can figure out which slit the signal photon went through. If you measure the idler in a way that erases which path information, you cannot. You run the experiment, you collect data, you record where every signal photon landed, then you look at the results. And here is what you find. If you sort the signal photons based on whether the idler measurement preserved or erased which path information, the two groups behave differently. The group where which path information was preserved shows no interference, just two clusters. The group where which path information was erased shows interference, alternating bright and dark bands, same signal photons, same double slit, same detector screen. The only difference is what you did with the idler photons afterward. And that difference, made after the signal photons had already been detected, changes the pattern. The interference appears or disappears depending on a measurement made later in time. This does not mean you can send a signal backward in time. The full data, before you sort it, looks random. No interference, no clusters, just noise. You only see the pattern when you divide the data into subsets based on the idler measurements. And you cannot do that division until the idler measurements are complete. So you cannot use this to send information to the past. You cannot change something that has already been observed in a way that lets you communicate backward. The interference only shows up in the correlations, in the relationship between what the signal photon did and what the idler photon did. But those correlations cannot be seen until both measurements are done. What it does mean, what the experiment forces you to confront, is that the past is not independent of the future. That the event that happened first, the signal photon hitting the screen, does not have a complete description until the event that happened later, the idler measurement, is also taken into account. The two events are entangled in time. The signal photon's behavior, whether it shows interference or not, depends on what you decide to do with the idler photon, even though the idler measurement happens later, even though the signal photon has already been detected. Physicists call this retrocausality, the idea that the future can influence the past, not in the sense that you can go back and change history, not in the sense that you can prevent your grandfather from being born, but in the sense that events that happen later can affect, or at least correlate with, events that already occurred. The which path information, the thing that determines whether you see interference, is not fixed when the particle goes through the slits. It is not fixed when the particle hits the detector. It is only fixed when the idler measurement is complete. And until that happens, the past event, the moment the signal photon was detected, does not have a definite character. It is in a kind of limbo, a superposition of interfered and not interfered. And what you do later determines which version becomes real. This is not an interpretation. This is what the data shows. The pattern you see on the signal detector depends on the idler measurement. That dependence is not a statistical fluke. It is not noise. It is a robust, repeatable result that has been confirmed in lab after lab. The delayed choice quantum eraser experiment was first performed in the late 1990s. It has been refined and extended since then. Every version shows the same thing. The future measurement affects the past pattern. Some physicists argue that this does not mean the future literally rewrites the past. They say that both events, the signal detection and the idler measurement, are just parts of a single quantum process. That the entire experiment, from the moment the photon pair is created to the moment the idler is measured, is one big entangled system. And you cannot talk about what the signal photon did in isolation from what the idler photon did, because they are not separate. They are two pieces of the same quantum state. The appearance of retrocausality in this view is just a consequence of entanglement. The signal and idler are connected. You cannot describe one without the other. And when you finally make all the measurements and sort the data, you see correlations that look like the future affected the past. But really, there was never a moment when the past was fully determined. The past was always provisional, always dependent on the rest of the experiment. That interpretation is less dramatic. It does not require throwing out causality, but it does require accepting that events do not have definite properties until the entire context, including future measurements, is complete, which is almost as unsettling because it means the past is not finished. It means that what already happened is still, in some sense, waiting for the future to decide what it was. Other physicists take the idea more seriously. They argue that quantum mechanics genuinely allows for retrocausality, that the future can constrain the past, that the arrow of time, the thing that makes causes precede effects, is not as fundamental as we thought, that at the quantum level, time is more symmetric, that the laws do not care which direction time flows, and the quantum eraser is evidence for that symmetry. It shows that information flow does not have to respect the order of events, that correlations can run backward as easily as forward. This is controversial. Most physicists are not ready to say that the future rewrites the past, but they are forced to admit that the quantum eraser does something strange, that it creates a situation where the pattern you see depends on measurements made later, and that dependence is real. It is in the data. It is not going away, and here is the thing. The quantum eraser is not the only experiment that shows this. There are other delayed choice experiments, variations where you decide, after a photon has already passed through a setup, whether to measure it as a particle or as a wave, and the result you get depends on your choice, even though the choice is made after the photon has already interacted with the apparatus. The photon, somehow, responds to your decision. It behaves like a wave if you set up the experiment to measure it as a wave. It behaves like a particle if you set up the experiment to measure it as a particle. And your choice can be made at the last possible second, after the photon has already committed, or so it seems, to one path or the other. John Wheeler, the same physicist who helped write the equation that removed time from cosmology, proposed one of these experiments in the 1970s. He called it the delayed choice experiment. The idea was to take a photon that had already decided whether to behave as a particle or a wave, and then, after it had decided, change the experiment, add or remove a piece of equipment that would force the photon to behave differently, and see what happens. The prediction based on quantum mechanics was that the photon would respond to the change, that its behavior would match the final setup, not the setup that was in place when it started. The experiment was eventually performed. The prediction was confirmed. The photon behaves according to the measurement you make, even if you decide what measurement to make after the photon has already passed through most of the apparatus. Wheeler took this seriously. He extended the idea to cosmology. He proposed a thought experiment where you observe a photon that has been traveling toward Earth for billions of years. The photon, emitted by a distant quasar, passes near a massive galaxy on its way here. The galaxy's gravity bends space-time, creating two possible paths the photon could take. One path around the left side of the galaxy, one path around the right side. By the time the photon reaches Earth, it has been traveling for billions of years. The choice of path, if there was a choice, happened long ago, but you can still decide, now, whether to measure which path the photon took, or to let it interfere with itself. If you measure which path, the photon will have taken one path or the other. If you look for interference, the photon will have taken both paths. Your measurement, made today, determines what the photon did billions of years ago. Not in your mind, in the universe. This is not science fiction. This is a serious proposal based on the same quantum mechanics that makes your computer work. And it suggests that the past of the universe, the history of every particle that has ever existed, is not fully determined until someone measures it. That the act of observation, the act of extracting information, completes the past, makes it real. Before that, the past is a superposition, a collection of possibilities, all of them equally real or equally unreal, until the future decides which one to make definite. If that is true, then time is not a line, it is a web, a tangle of correlations running forward and backward, connecting events that seem separated in time but are actually parts of a single quantum state. The past depends on the future depends on the past, and neither one is fully real until the whole web is measured, collapsed, observed. Until then, you are not moving through time, you are moving through a space of possibilities, and every measurement you make narrows that space, forces the universe to commit to a version of itself, but the version it commits to is not the only version that could have been, and the choice of which version becomes real is not made at the moment the event occurs, it is made later, sometimes much later, sometimes billions of years later. This has implications for free will that are even more disturbing than the block universe. The block universe said your future already exists, that your choices are already out there in space-time, frozen, waiting for you to experience them. That was bad enough, but at least your past was yours. At least the things you had already done were fixed. The quantum eraser suggests otherwise. It suggests that your past is still in play, that decisions you make tomorrow could, in some sense, influence what you did yesterday, not by changing the facts are recorded, but by changing which facts become real, by collapsing the wave function of your history into one configuration rather than another. This does not mean you can go back and undo a mistake. The macroscopic world, the world of tables and chairs and people and memories, does not show quantum effects like superposition and entanglement. Those effects get washed out by interactions with the environment, by decoherence. Once a measurement is made, once the wave function collapses, once the information is recorded in a way that cannot be erased, the past is fixed, at least for practical purposes. You cannot unbreak the egg, because breaking the egg involved trillions of particles interacting with the environment in ways that cannot be reversed. The which path information, at that scale, is permanently recorded. The interference is permanently destroyed. But at smaller scales, where decoherence has not yet set in, where the information is still erasable, the quantum eraser shows that the past is flexible, that it depends on the future, that the order in which events occur does not determine the order in which they become real, and if the universe is fundamentally quantum, if the macroscopic world is just an approximation that emerges from quantum rules applied to large numbers of particles, then the flexibility of the quantum past is not a quirk, it is a hint that time, even at large scales, is not as rigid as it looks, that the flow from past to future is something we perceive, something our brains construct, but not something the universe actually contains. Some philosophers have latched onto this. They argue that the quantum eraser proves that the future is open, that the past is not determinate. That reality is genuinely probabilistic, that the universe does not have a single history but a collection of histories, and that which history becomes real depends on what measurements are made. This is one interpretation of quantum mechanics. The many worlds interpretation takes it even further, saying that all possible histories are real, that the universe splits into parallel branches every time a measurement occurs, and that the branch you experience is just one of countless branches, all equally real, all playing out simultaneously in a vast multiverse of possibilities. In that picture, retrocausality is not a problem because there is no single past to rewrite. There are many pasts, and the one you remember is just the one you happen to be in. Other philosophers are less optimistic. They point out that the quantum eraser does not let you send information backward, that the interference pattern only shows up in correlations, not in the raw data, that you cannot use this effect to communicate with the past or to change anything that has already been observed in a controllable way. The retrocausality, if it exists, is not the kind you can exploit. It is not the kind that lets you go back and prevent a tragedy or fix a mistake. It is just a weird feature of the correlations between entangled systems. A feature that looks like the future is affecting the past, but might just be a consequence of treating time as more fundamental than it actually is. The debate is not settled. It may never be settled. But the experiments are clear. The quantum eraser works. The pattern changes depending on what you do later. And no matter how you interpret that, no matter what philosophical framework you use to make sense of it, you are forced to admit that the past is not as solid as everyday experience suggests, that the moment a particle hits a detector, that moment is not complete, it is not fully real. Not until the rest of the experiment is done, not until the future has had its say. And if the quantum eraser is telling us something true about the nature of time, if the dependence of past on future is not an artifact of measurement but a genuine feature of reality, then the timeline you thought you were living, the straight line from birth to death with the past behind you and the future ahead, that timeline is wrong. What you have instead is a web, a tangle, a structure where every moment is connected to every other moment, not just by the forward flow of cause and effect, but by correlations that run in both directions. The past shapes the future shapes the past, and neither one is finished until the whole web collapses into a single consistent history, which raises the question, when does that collapse happen? When does the wave function of the universe finally decide what the past was and what the future will be? The Wheeler-DeWitt equation suggests never, that the universe as a whole does not collapse, that it remains a timeless superposition of all possible histories. The quantum eraser suggests that collapse happens locally, that measurements made by observers or by any system that extracts information force parts of the universe to commit to definite states, but the universe as a whole, the totality of everything, never makes that commitment. It remains in limbo, a static mathematical object encoding every possible way things could be. And the version you experience, the history you remember, is just one thread in that object, one path through the web. Not the path, just a path. If that is true, then your past is not behind you, it is beside you, parallel to countless other pasts that could have been. And the future is not ahead of you, it is all around you, a cloud of possibilities waiting to be measured, to be collapsed, to be made real by the act of observation. You are not moving through time, you are collapsing wave functions, you are making measurements. You are narrowing the space of possibilities, and every measurement you make, every observation, every decision is both a consequence of what came before and a cause of what comes next, forward and backward, past and future, all tangled together in a web that has no beginning and no end, just structure, just correlations, just the static mathematics of a timeless universe that only looks like it is moving because you are inside it. And if the quantum eraser has shaken your confidence that the past is fixed, if it has made you question whether yesterday really happened the way you remember it, then you are ready for the next step. Because the quantum eraser is just a laboratory experiment, a handful of photons and detectors and entangled states. But there is a place in the universe where quantum mechanics and general relativity collide at full strength. A place where time does not just bend or vanish from the equations. A place where time, according to the math, stops completely. where the past, the present, and the future all pile up into a single point and cease to mean anything at all. That place is the center of our galaxy, and it has been sitting there 26,000 light-years away, waiting for us to understand what it is trying to tell us. So the quantum eraser showed us that the past is not as solid as it looks, that measurements you make now can influence or at least correlate with events that already happened, that the moment a particle was detected is not fully real until the rest of the experiment is done, that the future has a say in what the past was. That was unsettling enough. It said that time does not flow in one direction the way your intuition insists it must, that the arrow from cause to effect is not as rigid as everyday experience suggests, that the timeline you thought you were living on, the straight path from birth to death, with the past locked behind you and the future open ahead, that timeline is wrong. What you have instead is a web of correlations running forward and backward, connecting events that seem separated in time, but are actually parts of a single quantum state. That was disturbing, but it was also abstract. A handful of photons and detectors in a laboratory, a clever setup designed to tease out the weirdness buried in quantum mechanics. You could, if you wanted, dismiss it as a quirk of small systems, something that happens to particles but not to people, something that vanishes when you scale up to the macroscopic world where memories are recorded and eggs stay broken and the past feels permanent. But there is a place in the universe where the weirdness is not confined to laboratories, where the breakdown of time is not a subtle effect teased out by careful measurements of entangled photons, where time does not just bend or blur or become relative, where time, according to the equations, stops, where the past, the present, and the future collapse into a single point and cease to mean anything at all. That place is a black hole, and the nearest supermassive black hole, the one that has been sitting at the center of our galaxy since long before Earth existed, is called Sagittarius A star. And it is not hiding, it is right there, 26,000 light-years away. Invisible, yes, because it is black, because it does not emit light, because it is a hole in space, but surrounded by stars that orbit it so fast that you can watch them move year by year if you have a good enough telescope. And those stars are telling us that there is something enormous sitting at the center of their orbits, something with the mass of 4 million suns packed into a region smaller than the orbit of Mercury. Something that bends space-time so dramatically that the normal rules stop working, something that, if you could get close enough, would stop your clock entirely. Black holes are not hypothetical. They are not fringe physics. They are not speculative ideas cooked up by theorists with too much time on their hands. Black holes are predictions that fall out of Einstein's equations when you take them seriously, and they are confirmed by observation, by the motion of stars around invisible centers, by the radiation emitted by gas spiraling inward, by the gravitational waves detected when two black holes collide and merge, and, as of 2022, by direct images, not pictures of the black hole itself, because black holes are black, but pictures of the glowing ring of gas and light that surrounds them. The Event Horizon Telescope, a network of radio dishes scattered across the planet, working together as a single Earth-sized instrument, pointed at the center of our galaxy and produced the first image of Sagittarius A star, a bright ring with a dark center. The ring is light. The center is shadow, and the shadow is the event horizon, the point of no return, the place where, if you cross it, you are never coming back. The event horizon of Sagittarius A star is about 1 astronomical unit across. 1 astronomical unit is the distance from the Earth to the Sun, 93 million miles. That is the diameter of the point of no return. A sphere 1 hour wide sitting at the center of the Milky Way, bigger than the orbit of Mercury, smaller than the orbit of Venus. If you could somehow replace our Sun with Sagittarius A star, the event horizon would fill the inner solar system. Everything inside that sphere would be gone. Not destroyed in the sense of being blown apart, gone in the sense of being removed from the universe you can interact with. Cut off. Sealed behind a one-way door that lets things in but never lets them out. The reason black holes do this, the reason they warp space-time so dramatically, is mass. Specifically, mass packed into a very small volume. Take the mass of 4 million suns and compress it down until it fits inside a region the size of Mercury's orbit, and the gravitational pull becomes so strong that space-time itself cannot hold its shape. It collapses inward. It curves so sharply that paths through space-time, the trajectories that objects follow, all point inward. Once you cross the event horizon, every direction you could move, every path you could take, every possible future leads to the center. You cannot turn around. You cannot stop. You cannot hover. The geometry of space-time itself has been bent into a shape where the only way forward is down. General relativity, Einstein's theory of gravity, describes this with brutal precision. Gravity is not a force pulling you toward a massive object. Gravity is the curvature of space-time caused by that object. Mass bends space, it bends time, and the deeper you go into that curve, the more dramatic the effects become. Near Earth, the curvature is gentle. A clock at sea level ticks slightly slower than a clock on a mountaintop. But the difference is tiny, a few billionths of a second per day. You would never notice without an atomic clock. Near a black hole, the curvature is not gentle. It is extreme, and the effects are not tiny. They are overwhelming. Gravitational time dilation is one of the best confirmed predictions of general relativity. The closer you are to a massive object, the slower time runs relative to someone farther away. This is not a trick. This is not an illusion. This is not something that happens to your perception of time. This is something that happens to time itself. A clock sitting on the surface of a planet ticks slower than a clock in orbit around that planet. A clock in orbit ticks slower than a clock in deep space far from any mass. The difference is real. It is measurable. It is the reason GPS satellites have to correct for relativity. The satellites are farther from Earth's center than you are. Time runs faster up there. If the system did not account for that, your position would drift by several kilometers per day. Your phone compensates for Einstein's equations every time you ask for directions, but GPS satellites are in a weak gravitational field. The time dilation they experience is small. Near a black hole, the dilation is not small, it is extreme. Sit near the event horizon of Sagittarius A star, and time slows to a crawl relative to someone watching from a safe distance. To you, sitting near the horizon, time feels normal. Your watch ticks at the usual rate. Your heart beats at the usual rhythm. You do not feel slow, but if you could look back at the universe outside, you would see it speeding up. Stars would age and die in what feels like minutes. Galaxies would spiral and collide. The entire future history of the cosmos would unfold in fast forward. And to the person watching you from outside, you would appear to freeze. Your watch would slow. Your movements would become glacial. The light leaving your body would stretch, redshift, dim. Eventually, the signal would fade so much that you would become invisible. Not because you disappeared, because the time dilation became so extreme that the light takes longer and longer to climb out of the gravitational well. From the outside, you would appear to approach the horizon, but never quite reach it. You would hang there, frozen, fading, until the universe ended. That is what general relativity says happens, and it is not because the math is broken. It is because space-time near a black hole is bent so sharply that time, as measured by distant observers, stretches to infinity at the horizon. The event horizon is not a wall. It is not a surface. It is a mathematical boundary, a place where the geometry of space-time changes character. Outside the horizon, you can escape. Light can escape. Information can get out. Inside the horizon, nothing escapes, not because there is a barrier, because every direction points inward. The future, for anything inside, lies toward the center. There is no path that leads back out. Not because something is stopping you, because the paths do not exist. Space-time itself has been folded into a shape where the only future is the singularity. The singularity is the center, the place where, according to the equations, all the mass of the black hole is concentrated, not spread out over a region, concentrated into a point with zero volume and infinite density, a place where the curvature of space-time becomes infinite, where the equations of general relativity, the same equations that predict black holes in the first place, stop working. They do not give you an answer, they give you infinity, and infinity in physics is not an answer. It is a signal that something has gone wrong, that the theory has reached the edge of its domain, that the description is incomplete. Physicists do not believe the singularity is a real thing, not in the sense of an infinitely dense point actually existing in nature. What they believe is that the singularity is a placeholder, a warning sign, a spot on the map marked "Here be dragons." The equations are telling you that something happens at the center of a black hole that general relativity cannot describe, that you need a better theory, a theory that combines general relativity with quantum mechanics, a theory of quantum gravity, and we do not have that theory, not yet, not in a complete form. We have hints, we have candidate frameworks, string theory, loop quantum gravity, but none of them are finished. None of them make predictions we can test, and all of them agree on one thing: the classical picture, the infinitely dense point, is wrong. The singularity is not a point. It is a region where space-time itself breaks down, where the usual notions of distance and time and cause and effect stop making sense, where the question "what happens next" becomes meaningless because next implies time, and time at the singularity is not a thing that exists. Here is what that means in practical terms. Imagine you are falling into Sagittarius A star. You cross the event horizon. From your perspective, nothing dramatic happens. You do not hit a wall. You do not feel a jolt. You just cross an invisible boundary and keep falling. Behind you, the universe you left is still there. You can still see it. The stars are still shining. But the light from those stars is blue-shifted now, compressed by the curvature of space-time into higher and higher frequencies. The longer you fall, the more compressed it becomes. Eventually, the entire history of the universe outside would pile up into a single blinding flash of radiation. But you would not have time to watch that, because the tidal forces would tear you apart long before you reached the singularity. Tidal forces are a consequence of gravity being stronger on one side of your body than the other. If you are falling feet first toward a black hole, your feet are closer to the center than your head. They experience stronger gravity. They accelerate faster. The result is that you get stretched. Your body is pulled into a long, thin strand. Physicists call this spaghettification. It is not a joke. It is a real effect. And near the singularity of a black hole, the tidal forces become so strong that no material, no matter how strong, can hold together. Atoms are pulled apart, nuclei are pulled apart. The structure of matter itself unravels. But let us ignore that for a moment. Let us pretend you are made of something indestructible. Let us follow you all the way to the singularity and ask what happens to time. The answer, according to general relativity, is that time stops, not from the perspective of someone watching from outside, from your perspective, the person falling in. As you approach the singularity, the curvature of space-time becomes so extreme that the usual distinctions between space and time blur. Time, the thing that was ticking forward in a predictable rhythm, starts to behave like space. Space, the thing you could move through in any direction, starts to behave like time. You lose the ability to move freely. Every direction you could go, every path through space-time, points toward the singularity. The singularity is not just in front of you, it is in your future. It is the only future you have, and the closer you get, the less sense it makes to ask when you will arrive. Because when implies time, and time, in the geometry near the singularity, has stopped being the thing that separates past from future. It has become something else, something tangled up with space in a way that the equations cannot untangle. The singularity in this picture is not a moment, it is not an event. It is a place where time ends, not ends in the sense that it stops ticking, ends in the sense that it ceases to be a meaningful concept. The question, what happens after the singularity, is not a question physics can answer, because after implies time, and time is part of the structure that is breaking down. The singularity is not just the center of the black hole. It is the edge of space-time itself, the place where the fabric runs out, where the map ends, where the equations, having taken you as far as they can, shrug and say, "We do not know what comes next." This is not comfortable, and it is not speculative. This is a direct consequence of taking general relativity seriously. The equations predict black holes. The equations predict event horizons. The equations predict singularities. And the equations predict that time, near the singularity, stops being a thing you can describe with the usual tools. Physicists hope that a theory of quantum gravity will fix this, that it will replace the singularity with something less pathological, a region of extremely high but finite curvature, a quantum foam, a bounce, something that avoids the infinities and keeps the equations working. But until we have that theory, until we can test it, the singularity remains, a hole in our understanding, a place where the rules break down, a place where time, the thing we have been chasing through relativity and quantum mechanics and the block universe and the Wheeler-DeWitt equation, finally gives up and ceases to exist. Sagittarius A star is not unique. There are supermassive black holes at the centers of most galaxies. Some are larger, some are smaller, some are actively feeding, surrounded by glowing disks of gas spiraling inward at a significant fraction of the speed of light. Some, like Sagittarius A star, are quiet, not feeding much, just sitting there, warping spacetime, bending the orbits of nearby stars into tight ellipses that swing past the event horizon at thousands of kilometers per second. We have watched those stars. We have tracked their orbits for decades. One of them, called S2, orbits Sagittarius A star every 16 years. Its closest approach brings it to within 17 light-hours of the event horizon. At that distance, moving at more than 7,000 kilometers per second, the star experiences gravitational effects strong enough to test general relativity in ways that were impossible before. And every test confirms the theory. The orbit matches the predictions. The redshift matches the predictions. The time dilation matches the predictions. Sagittarius A star behaves exactly the way a 4 million solar mass black hole should behave. And that means the singularity is there, hidden behind the event horizon, inaccessible but real, or at least as real as the equations say it is. The Event Horizon Telescope's image of Sagittarius A star is not just a pretty picture. It is a confirmation, a piece of evidence that what the equations predict actually exists. The bright ring in the image is light, photons emitted by gas orbiting the black hole. Some of those photons escape, some spiral inward and are lost. The boundary between escaping and not escaping is the photon sphere, a region just outside the event horizon where light can orbit the black hole. Inside the photon sphere, light cannot escape. It is doomed. And the dark center of the image, the shadow, is the region where no light can get out. That shadow is slightly larger than the event horizon itself because of the way spacetime is curved, but it marks the boundary, the point of no return, the place where time, for an outside observer, stretches to infinity, where clocks stop, where signals fade, where the universe you came from recedes into the past, and you are left with only the singularity ahead. This is not a metaphor. This is not an analogy. This is what happens, and it is happening right now, at the center of this galaxy, at the center of every galaxy with a supermassive black hole. Time, near those objects, is not flowing the way it flows here. It is stretched, warped, in some frames, stopped entirely. And at the singularity, if the singularity is real, time is gone, not slowed, not dilated, gone, removed from the description, erased from the equations. The singularity is a place, or an event, or a boundary, where the concept of time ceases to apply, where asking what happens next is like asking what is north of the North Pole. The question is grammatically correct, but physically meaningless. Some physicists have taken this seriously. They have asked whether the singularity, or something like it, might be a clue, a hint about the true nature of time. If time can stop, if it can cease to be a meaningful concept under extreme conditions, then maybe time was never fundamental. Maybe time is something that emerges in certain regimes, under certain conditions, and disappears when those conditions are no longer met. The block universe suggested that time is a coordinate, a dimension, not a flow. The Wheeler-DeWitt equation suggested that time is absent from the most complete description of the universe. The quantum eraser suggested that time is not as directional as it looks. And now Sagittarius A star, sitting at the center of the galaxy, is suggesting that time can end, that there are places in the universe where the usual rules do not apply, where the timeline breaks, where the past and future collapse into a single point and stop being distinguishable. This is where the silence gets loudest. Because if time can end at a singularity, if it can stop being a thing that exists, then what does that say about the rest of the universe? What does it say about the time you are experiencing right now, the flow from past to future that feels so real, so undeniable, so central to everything you are? If time is something that can be turned off, something that vanishes under the right conditions, then it is not a fundamental feature of reality. It is conditional, it is emergent, it is something that appears in certain contexts and disappears in others. And the context you are in right now, the macroscopic world of planets and stars and people and clocks, is just one context, not the only one, not the fundamental one, just the one you happen to be in. Sagittarius A star is also surprisingly quiet. For a supermassive black hole, it is not doing much. Some black holes are surrounded by accretion disks so bright they outshine entire galaxies. They are called quasars, and they are some of the most luminous objects in the universe. Sagittarius A star is not a quasar. It is barely eating. The gas falling into it is sparse. The radiation it emits is faint. If you could see it with your eyes, it would be invisible, not because it is far away, because it is not glowing. The Event Horizon Telescope had to use radio waves to image it, long wavelength light that can pierce through the dust and gas filling the galactic center, and even then the signal was faint. The telescope had to stare for hours, combining data from dishes all over the world to produce the image. But the image is there, the shadow is there, the event horizon is there, and the singularity hidden at the center is there, or at least something is there. Something the equations cannot fully describe, something where time stops. Here is the thing. You do not have to fall into a black hole to see the effects. You just have to get close. Close enough that the time dilation becomes noticeable. And noticeable in this context means measurable with the instruments we have. The stars orbiting Sagittarius A star are experiencing time dilation. Not enough to freeze them, not enough to stretch their clocks to infinity, but enough that we can measure it. Enough that their light is redshifted by the gravitational field. Enough that their orbits show the fingerprints of relativity. And if we could put a clock on one of those stars, if we could compare it to a clock far from the black hole, the clocks would disagree. The one near the black hole would tick slower, not much slower, but measurably slower. And the closer you got, the larger the difference would become, until, at the event horizon, the difference would become infinite. The clock near the horizon would stop entirely from the perspective of the distant observer, not because the clock broke, because time itself, in that geometry, in that frame, has stretched to the breaking point. This raises a question that nobody has a good answer to. If time stops at the event horizon, if an outside observer never sees anything cross the horizon, if infalling matter just hangs there, frozen, fading, redshifting into invisibility, then in what sense does the black hole grow? How does it accrete mass if the mass never crosses the horizon? The answer is that it depends on your frame of reference. From the perspective of the infalling matter, the crossing happens. The event horizon is past, the singularity is approached. From the perspective of a distant observer, the crossing never happens. The matter freezes at the horizon and stays there forever. Both perspectives are valid. Both are correct descriptions of the same event, just from different points of view. And general relativity does not pick sides. It says both observers are right. The universe does not have a single story about what happens. It has multiple stories, one for each observer, and all of them are true. This is the same lesson relativity has been teaching since 1905. There is no universal now. There is no single timeline that everyone agrees on. There is only a collection of local timelines, one for each observer, each describing the universe from their own point of view. And near a black hole, those timelines diverge so dramatically that they stop overlapping. One observer sees matter frozen at the horizon, another sees matter falling through and reaching the singularity, and both are right. Because right is frame-dependent, because time is frame-dependent, because the universe does not care which frame you happen to be in. It lets each frame have its own version of events, and the versions do not have to match. If that sounds like the universe is fragmented, like there is no single objective reality that everyone can agree on, that is because the universe is fragmented. Or at least, the usual notion of objective reality, the idea that there is a single correct answer to the question what is happening right now, that notion does not work. What is happening right now depends on who is asking, depends on where they are, depends on how fast they are moving, depends on how deep they are in a gravitational well and near a black hole. The dependence becomes so extreme that the question stops having a single answer. Time, the thing that was supposed to order events into a sequence everyone could agree on, has broken. Not because the equations failed, because the equations worked, because they followed the geometry of space-time to its logical conclusion, and the conclusion is that time is not universal, time is local, time is observer-dependent, and under extreme conditions time can stop, and Sagittarius A star is not the most extreme case. There are black holes with higher spin, black holes with more mass, black holes surrounded by denser accretion disks, black holes where the tidal forces are stronger, the time dilation more severe, the approach to the singularity more violent, and every one of them is a laboratory, a natural experiment testing the limits of general relativity, pushing space-time to the breaking point, showing us what happens when you take the equations seriously and follow them all the way to the edge. And the edge is a place where time stops, where the past and future pile up into a single point, where the question what happens next becomes meaningless, where the timeline you thought you were living on terminates, not because you died, not because the universe ended, because the geometry of space-time ran out of room, because the coordinates you were using to describe reality stopped working, because time, the thing you thought was fundamental, turned out to be conditional, a feature of certain regions of space-time, a property of certain frames of reference, not a universal backdrop, not a river flowing from past to future, just a coordinate, just a label, just a way of organizing events that works in most places but breaks down in some, and a black hole is one of those places. So here is where we are. Relativity said time is not universal. The block universe said past, present, and future all exist simultaneously. The Wheeler-DeWitt equation said time is absent from the most fundamental description of the universe. The quantum eraser said the past is not fixed. And now Sagittarius A star, sitting at the center of the Milky Way, is saying that time can stop, that there are places not far away, not in some hypothetical universe, but right here in this galaxy, where time ceases to be a thing that exists, where the flow from past to future ends, where the timeline breaks, where the equations that describe reality lose their grip and admit that they do not know what comes next. And yet here you are, reading this, experiencing time as a flow, feeling the present moment as something unique, something real, something different from the past and the future. The universe is telling you, through its equations and its experiments and its black holes, that time is not what it seems, that the flow is an illusion, that the present is not a universal moment but a local frame, that the past is not fixed and the future is not open, and the timeline you thought you were living on is not a line at all but a coordinate, a label, a bookkeeping device. And still, you feel time passing. Still, you remember yesterday and plan for tomorrow. Still, the sensation of now, the feeling that this moment is special, refuses to go away. So where is that feeling coming from? If time is not fundamental, if the universe does not actually contain a flow, if the equations describing reality at its deepest level do not include a variable for time, then why does it feel like time is passing? Why does the present feel different from the past? Why do you remember one and not the other? Why does cause precede effect in your experience even though the Wheeler-DeWitt equation treats all moments equally? The answer is that the feeling is not coming from the universe, it is coming from you, from your brain, from the way your nervous system processes information, from the architecture of memory and perception and consciousness. The flow of time is not a feature of reality. It is a feature of how you experience reality. And if you want to understand why time feels real even though the universe says it is not, you have to look inside your own head. You have to ask what your brain is doing when it constructs the sensation of now. And the answer, it turns out, is that your brain is lying to you. Not maliciously, not randomly, but systematically, deliberately, in a way that makes perfect sense once you understand what the brain is built to do. And that is where we are going next. So Sagittarius A star showed us that time can stop, that there are places in the universe, not hypothetical places, not mathematical abstractions, but actual locations sitting at the center of galaxies, including our own, where the geometry of space-time warps so dramatically that time ceases to be a meaningful concept, where clocks freeze, where the future collapses into the singularity and the past stretches to infinity, and the question what happens next becomes meaningless because next implies time and time has run out. That was disturbing, but it was also distant. 26,000 light-years away, hidden behind an event horizon, sealed inside a region of space you could never visit and survive. You could, if you wanted, file it away as an exotic edge case, a breakdown that happens in extreme conditions but has nothing to do with your life, with your morning coffee, with the clock ticking on the wall, with the sensation you have right now that time is passing, that the present moment is real, that you are living through something that is happening now and not a second ago or a second from now, but now. Except the sensation is wrong. Not wrong in the sense that you are hallucinating, wrong in the sense that what you are experiencing as now is not actually now, it is the past. Your brain is showing you an edited reconstruction of events that already happened. A highlight reel assembled from fragments of sensory data that arrived at different times, were processed at different speeds, and were stitched together into a coherent narrative and presented to your consciousness as if they were all happening at the same moment. The now you are experiencing is a fabrication, a story your brain tells you, not maliciously, not randomly, but systematically, deliberately. Because that is what brains do. They take noisy, delayed, fragmented input from the world and turn it into something that feels smooth and immediate and real. And the cost of that transformation is that the thing you experience as the present moment is not the present. It is the past, dressed up to look like now. This is not philosophy, this is neuroscience, and the evidence for it is overwhelming. The first crack in the illusion appeared in the 1980s. A physiologist named Benjamin Libet was working at the University of California, San Francisco, running a series of experiments designed to measure the timing of conscious decisions. Libet was not trying to prove that free will is an illusion. He was not trying to dismantle the concept of now. He was just trying to answer a straightforward question. When you decide to move your hand, when does that decision actually happen? Does it happen at the moment you feel yourself deciding, or does it happen earlier, beneath the surface, in the unconscious machinery of your brain, before the feeling of decision ever arrives? The setup was simple. Libet asked participants to sit in front of a clock, not a normal clock. A special one, with a dot sweeping around the face faster than a second hand, so that participants could report the exact moment they felt the urge to move. They were told to flex their wrist whenever they wanted. No external cue, no prompt. Just wait until you feel like moving, then move. And while they were sitting there waiting, deciding, moving, Libet was recording two things. First, the electrical activity in their brains using electrodes placed on their scalps. Second, the exact moment they reported feeling the urge to move, marked by the position of the dot on the clock. What Libet found was unsettling. The brain activity came first, not a little bit first, a lot first. There was a specific pattern of electrical activity, a buildup of voltage that Libet called the readiness potential, and it appeared in the brain about 550 milliseconds before the person moved their wrist. More than half a second. That was not surprising. The brain has to prepare for movement. Muscles do not just fire on their own. They need signals from the motor cortex. The motor cortex needs input from other regions. The whole system has to coordinate. A delay of half a second for all of that to happen is reasonable. The disturbing part came when Libet compared the timing of the readiness potential to the timing of the conscious decision. Participants reported feeling the urge to move about 200 milliseconds before they actually moved, 0.2 of a second. That felt right. That matched their subjective experience. You decide to move, then a moment later you move. Decision first, action second, cause and effect. Except the readiness potential, the brain activity that actually initiated the movement, started 350 milliseconds before the conscious urge. Before you felt like you were deciding, your brain had already decided. The feeling of decision, the moment you experienced as the instant you chose to move, came after the choice had already been made. Not by much, a third of a second, but that third of a second is enough to flip the story upside down. You did not decide and then your brain acted. Your brain acted and then you experienced the decision. Libet published the results in 1983. The paper was careful. Libet did not claim he had disproven free will. He suggested that consciousness might still play a role, maybe as a veto mechanism. Maybe the unconscious brain prepares the action, and then consciousness gets a brief window to stop it before it happens, a last-minute override. That interpretation left room for some version of agency, some sense in which you are still in control, but the damage was done. The data was clear. The feeling of deciding came after the brain activity that initiated the decision. Conscious will, the thing you experience as the moment you choose, is not the cause of your actions. It is an after-the-fact report. A story your brain tells you about something that already happened, and it is not just movement. Later experiments extended the finding to other kinds of decisions. When you decide to press a button, when you decide to speak, when you decide to shift your attention from one thing to another, the same pattern shows up. Brain activity precedes conscious awareness. The decision is made before you experience making it. And the gap is not tiny. It is measurable. It is consistent. It is large enough that researchers can, in some cases, predict what you are about to decide before you know it yourself. They can watch the pattern of activity in your brain and tell you, with better-than-chance accuracy, which button you are about to press. Not because they are reading your mind in some mystical sense, because your mind has not caught up yet. The decision is already encoded in your neural activity. It just has not reached consciousness. You have not felt it yet, but it is there, waiting. This is deeply uncomfortable. Most people, when they first hear about Libet's experiments, try to find a way around the implications. Maybe the participants were not really deciding. Maybe the task was too simple. Maybe flexing your wrist is not a real decision. Maybe if you tested something more meaningful, something with stakes, the timing would be different. But follow-up studies have tested more complex decisions, and the pattern holds. The brain prepares, then consciousness experiences. The order does not reverse. The gap does not close. Some neuroscientists argue that this does not eliminate free will. They say that the readiness potential is not a decision. It is preparation, a kind of neural noise, a build-up of random activity that eventually crosses a threshold and triggers an action. In that view, the conscious experience of deciding is still real. It is just not the initial spark. It is the moment when the threshold is crossed and the action becomes inevitable. Other neuroscientists are less generous. They say the experiments show exactly what they appear to show. That consciousness is not in the driver's seat, that the feeling of control is an illusion, that you are a passenger in your own life, watching a movie of decisions that were made by unconscious processes and presented to you as if you had made them. The debate is not settled. It may never be settled, but the data is there, and it keeps saying the same thing. The moment you experience as now, the moment when you feel yourself deciding, is not the moment the decision happens. It is the moment you become aware of a decision that already happened. Your experience lags, your consciousness is delayed, and the delay is long enough that the present you are experiencing is not the present, it is the past. That delay is not limited to decisions. It applies to everything you perceive, every sight, every sound, every touch. The world you are experiencing right now, the one that feels immediate and real and present, is a reconstruction, an edited summary of events that already occurred. And the delay, depending on what you are perceiving, can be anywhere from a few dozen milliseconds to half a second or more. Here is why. Your senses do not work at the same speed. Light travels fast. When a photon hits your retina, the signal reaches your brain in about 50 milliseconds. Sound is slower. When a sound wave reaches your ear, it takes about 20 milliseconds for the signal to reach your brain, but that is just the time it takes for the signal to arrive. Processing takes longer. Your brain has to figure out what the signal means. It has to identify edges, colors, shapes, movements. It has to separate sounds into sources. It has to filter out noise. All of that takes time. And different parts of the signal are processed at different speeds in different regions of the brain. The result is that the raw sensory data arrives in fragments, scattered across time, and your brain has to wait until enough fragments have arrived to assemble them into a coherent picture. This is called temporal binding. Your brain takes inputs that arrived at different times and binds them together, presenting them to consciousness as if they happened simultaneously. You see someone clap their hands, and you hear the sound of the clap, and your brain makes it feel like the sight and the sound occurred at the same instant, but they did not. The light from their hands reached you first. The sound arrived later. Your brain waited for both signals to be processed, then lined them up and delivered them to consciousness as a single event. The delay between the actual clap and your experience of the clap can be 100 milliseconds or more, a tenth of a second. That does not sound like much, but a tenth of a second is a long time in neural terms. A lot can happen in a tenth of a second, and all of it happens before you experience anything. The brain is not just lining up signals, it is filling in gaps, smoothing over inconsistencies, predicting what should be there and inserting it if the data is missing. Your visual field has a blind spot where the optic nerve connects to the retina. There are no photoreceptors there, no signal, a hole in your vision, but you do not see a hole. You do not see a black spot or a blur or an empty patch. You see a seamless image because your brain, without asking permission, fills in the blind spot with whatever it thinks should be there based on the surrounding context. It invents data. It makes up part of the world you are looking at. And it does this so smoothly, so automatically, that you never notice. The fabrication is invisible. This happens everywhere. Your peripheral vision is terrible. Low resolution, no color, barely able to detect motion. But you do not experience your peripheral vision as blurry. You experience it as clear because you are not actually seeing your periphery most of the time. You are seeing a memory of it, a cached image that your brain updates only when something changes. The rest of the time, your brain just replays the last good frame and makes you feel like you are seeing a full high-definition panorama when what you are actually seeing is a narrow spotlight surrounded by blurry guesses. And then there is the delay, the half-second gap between the world and your experience of it. The brain does not present sensory data to consciousness as soon as it arrives. It waits, it collects. It processes, it edits, and then, when enough information has been gathered and sorted and packaged, it delivers a finished product, a moment of experience, a slice of now. But that now is not now, it is the past, events that already happened, sensory signals that already arrived, decisions that were already made. All of it bundled together, smoothed over, time-stamped with the label present, and handed to consciousness as if it were live. The gap is not constant, it varies. Fast reactions, like pulling your hand away from something hot, bypass consciousness entirely. The signal goes from your skin to your spinal cord and back to your muscles without ever reaching your brain. You move first. You feel the pain second. Consciousness arrives late to the party and experiences the decision to pull away as if it happened in the moment, but the decision was made by a reflex arc that has no connection to your conscious mind. You had no say, your body acted. Your consciousness caught up later and took credit. For slower, more deliberate actions, the delay is longer. When you read a sentence, when you listen to a conversation, when you watch something happen, your brain is holding on to pieces of the input, buffering them, waiting for enough context to interpret what is happening before presenting it to consciousness. This is why you can sometimes realize, a moment too late, that someone just said something surprising. The words entered your ears half a second ago. Your brain processed them, but the meaning did not reach consciousness until just now. And now you are reacting to something that, from the perspective of the outside world, already happened. You are living in the past. This is not a malfunction. This is the system working as designed. The brain is not built to give you a live feed of reality. It is built to give you a usable model of reality. A model that is stable, coherent, predictable. A model where causes precede effects, where objects persist, where the world makes sense. And to build that model, the brain has to lie. It has to smooth over delays. It has to fill in gaps. It has to take noisy, fragmented, contradictory input and turn it into something that feels seamless. The cost is accuracy. The cost is immediacy. What you get instead is stability. You get the feeling that you are experiencing the present moment, that you are here now in this instant. But the instant you are experiencing is not this instant. It is an instant that already passed, a memory labeled now. Some researchers have measured the delay directly. They set up experiments where participants are asked to report the timing of events, a flash of light, a sound, a touch, and then they compare the reported timing to the actual timing. The gap is consistent. Consciousness lags. The conscious experience of an event happens after the event itself, and the lag is not negligible. It is not a few milliseconds that you could dismiss as noise. It is hundreds of milliseconds, long enough that the world you are experiencing is noticeably out of date. Long enough that if you were trying to interact with something fast, something that requires real-time responses, your conscious experience would be too slow to keep up. Which is why fast reactions do not involve consciousness. Consciousness is too slow. It is a post-processing system, a review board, not a controller. The number you hear most often is 500 milliseconds, half a second. That is the popular figure, the one that shows up in articles and talks and books. The idea is that your conscious experience of the present moment is delayed by about half a second, that everything you see, hear, feel is arriving at consciousness 500 milliseconds after it actually happened. That figure comes from studies like Libet's and from experiments on sensory binding and reaction time. It is not a universal constant. The delay varies depending on what you are doing, how much processing is required, how much attention you are paying, but half a second is a reasonable ballpark, a reasonable estimate of how far behind consciousness is running. Think about what that means. Right now, as you are reading this, your experience of this moment is half a second old. The words you are reading entered your eyes half a second ago. The sounds around you reached your ears half a second ago. The feeling of the chair beneath you, the temperature of the air, the position of your body, all of that was sensed half a second ago. Your brain has been processing it, assembling it, stitching it into a coherent picture, and now, half a second later, It is presenting that picture to consciousness as the present. You are living in the past. You have always been living in the past. The present, the thing that feels so immediate and so real, is a delayed broadcast, a replay, a summary of events that already occurred, packaged and delivered with a label that says now. And here is the strangest part. The brain does not just delay your experience, it also reorders it. It takes events that happened in one sequence and presents them to consciousness in a different sequence. Or it blurs the sequence entirely, making events that happened at different times feel like they happened simultaneously. This is necessary. If the brain presented sensory data to consciousness in the order it arrived, the world would feel chaotic. Sounds would lag behind sights. Touch would lag behind sound. Every movement you made would feel disjointed, fragmented, out of sync. So the brain waits. It holds on to the data until it has enough to construct a coherent moment. And then it presents that moment as if all the pieces happened at once, as if they were synchronized, but they were not. They were scattered across time, and your brain lied to you about the order to make the world feel stable. There are experiments that demonstrate this. One of the most striking is called the flash lag effect. You show someone a moving object, a dot drifting across a screen. At some point, you flash a second object, a static shape, right next to the moving dot. The flash and the dot are perfectly aligned in space. They are in the same location at the same instant. But when people report what they saw, they say the moving dot was ahead of the flash. The dot appeared to be farther along its path than the static shape, even though they were in the same place at the same time. Why? Because the brain is predicting the motion of the dot. It is extrapolating where the dot will be a few dozen milliseconds into the future and presenting that prediction to consciousness as the current position. Meanwhile, the flash, being unexpected, is processed without prediction. It gets the default delay. So when consciousness experiences the moment, the dot has already been moved forward in time by the brain's prediction system, and the flash is where it actually was. The result is that two things that happened at the same time are experienced as happening at different times. The brain reordered them. This is not rare. This is how the brain works. Prediction, extrapolation, reordering, filling in, all of it happening beneath the surface, invisible to consciousness, constructing the experience of now from fragments of the past. And the reason you do not notice is that you have nothing to compare it to. You cannot step outside your own consciousness and see the world as it actually is, unfiltered, unprocessed, with no delay. The only world you have access to is the one your brain shows you. And that world, by design, feels immediate. It feels present. It feels real. But it is not. It is an edited summary, a highlight reel, a fabrication. Some philosophers have seized on this as evidence that the present moment is an illusion, that there is no such thing as now, even in subjective experience, that what we call the present is just a moving window, a spotlight sweeping across a static timeline, illuminating one moment after another, and the moment being illuminated is not the moment you are in, it is a moment you already passed. You are always looking backward, always experiencing the past. The present, the thing you think you are living through right now, does not exist. It is a label your brain applies to recent events to make them feel current. That view has support from physics. Relativity said there is no universal now. The block universe said past, present, and future all exist simultaneously. The Wheeler-DeWitt equation said time is not fundamental. And now neuroscience is saying that even your subjective experience of now, even the private, personal sensation that you are living through this moment right here, right now, even that is a construct, a fabrication, a story, not a lie exactly, but not the truth either. A useful fiction, a way of organizing sensory data into something that feels coherent and navigable, and the price of that coherence is accuracy. The price is immediacy. You get a stable, predictable world, but the world you get is not the world that is, it is the world that was, a moment ago, half a second ago, long enough that by the time you experience anything, it is already over. This has implications for free will that go beyond Libet's experiments. If consciousness is delayed, if the feeling of deciding comes after the decision is made, and if the experience of the present is a reconstruction of the past, then what exactly is consciousness doing? What role is it playing? Some neuroscientists argue that consciousness is an observer, that it watches the output of unconscious processes and constructs a narrative, a sense of self, a story about who you are and what you are doing and why. And that story is useful. It helps you plan. It helps you communicate. It helps you reflect on past actions and imagine future ones. But the story is not the driver. It is the passenger. It is along for the ride, watching, narrating, but not steering. Other neuroscientists argue that consciousness does have a role, even if it is delayed. That the veto mechanism Libet proposed is real. That unconscious processes prepare actions, and consciousness gets a brief window to approve or cancel them before they execute. In that view, free will is not about initiating actions, it is about stopping them, about saying no, about overriding the defaults. That still leaves room for agency, still leaves room for the feeling that you are in control. But it is a much weaker form of control than the one most people assume they have. You are not choosing what to do, you are choosing what not to do. And even that choice is happening in a narrow window, a few dozen milliseconds, between the moment the unconscious brain commits to an action and the moment the action is executed. And if that sounds unsatisfying, if it feels like the kind of free will you are left with is barely worth calling free will at all, you are not alone. A lot of people find this deeply troubling. The idea that your conscious experience is a delayed, edited, fabricated reconstruction of events that already happened. That the decisions you think you are making were already made by processes you have no access to. That the present moment you are living through is not present at all, but past. That everything you experience is a summary, a highlight reel, a story your brain tells you after the fact. And the story is so convincing, so seamless, so immediate, that you never question it. You never notice the delay, you never see the edits, you just experience the final product and assume it is reality. But it is not, it is a model, a simulation, a user interface, and the interface is designed to hide the complexity underneath, to hide the delays, the gaps, the reordering, the predictions, to present you with something smooth and stable and coherent, something that feels like now, and the cost of that feeling is the truth. The truth is that now does not exist, not in your subjective experience, not in the physical universe. The present is a moving target, a label applied to events that already occurred, a coordinate in space-time that has no special status, and your experience of that present, the thing that feels so real, so undeniable, is a fabrication, a construct, a story, a lie. Not a malicious lie, a necessary one. Because without that lie, the world would be chaos. You would experience sensory data as it arrived, scattered and noisy and out of sync. You would have no sense of continuity, no sense of self, no sense of time passing. The brain gives you all of that. It gives you the feeling of flow, the feeling of now, the feeling that you are here in this moment experiencing things as they happen. And the price is that none of it is true. The flow is an illusion. The now is a reconstruction, and the experience is a fabrication. And if the brain can fabricate the present, if it can take scattered fragments of the past and assemble them into something that feels immediate and real, then what else is it fabricating? What else are you experiencing that is not actually there? How much of your reality is a construct? How much is invented by the machinery between your ears? And if the answer is all of it, if everything you experience is a model built by your brain rather than a direct perception of the world, then what are you actually experiencing? Are you experiencing the universe, or are you experiencing your brain's best guess about the universe? And if it is a guess, how good is the guess? How accurate? How much does it leave out? How much does it distort? These are not easy questions, and neuroscience does not have complete answers. But what it does have is evidence. Evidence that the brain is not a passive receiver. It is an active constructor. It predicts, it fills in, it smooths over, it delays, it reorders, it fabricates, and the result is the experience you are having right now, the sensation of being here, the sensation of now, the sensation that time is passing and you are living through it, all of it constructed, all of it delayed, all of it a story, and the story your brain is telling you right now, the one that says you are reading these words in the present moment, is wrong. You read these words half a second ago. Your brain is just now getting around to showing them to you. The present you are experiencing is the past. And the past, according to the quantum eraser, is not even fixed. And the future, according to the block universe, already exists. And time, according to the Wheeler-DeWitt equation, is not fundamental. And now your brain, the thing you thought you could trust to at least give you an accurate picture of your own experience, is telling you that even the feeling of now is a fabrication, that the timeline you are living on is a construct, that the flow of time you feel so clearly is something your nervous system is manufacturing moment by moment, because that is the only way to turn noisy, delayed sensory input into a coherent, navigable experience. So here is where we are. The universe says time is not fundamental. Your brain says the present is not real. Physics says the past and future exist simultaneously. Neuroscience says your experience of now is a half-second-old reconstruction, and yet you are still here, still feeling time pass, still experiencing the present as something immediate and real. The contradiction is total. The evidence is overwhelming. And the silence, the reason physicists and neuroscientists do not talk about this more loudly, is starting to make sense. Because once you say it out loud, once you admit that time does not exist and the present is an illusion and your experience is a fabrication, you are left with a question that nobody knows how to answer. If all of that is true, then what is actually happening? What is the universe actually doing? And what are you? So your brain has been lying to you. Not maliciously, not randomly, but systematically. The present moment you experience, the now that feels so immediate, so real, so undeniably current, is a fabrication, a half-second-old reconstruction of events that already happened. Your consciousness is a delayed broadcast, a highlight reel assembled from fragments that arrived at different times and were stitched together into a coherent story and stamped with a label that says present. You are living in the past. You have always been living in the past. And the feeling that you are here, right now, experiencing this moment as it unfolds, is something your nervous system manufactures for you, because that is the only way a biological organism can navigate a universe that, at its foundation, does not contain a now at all. That was disturbing enough, but it leaves one question still hanging in the air, one piece of the puzzle that has not been addressed. If time is not fundamental, if the universe is a timeless block and the Wheeler-DeWitt equation erases time from the most complete description of reality and quantum mechanics, allows the future to influence the past, and your brain constructs the present out of delayed sensory data. Then what about the arrow? What about the thing that everyone, physicist or not, agrees on? That eggs break but do not unbreak. That coffee cools but does not spontaneously heat up. That memories point backward, never forward. That causes precede effects. That the universe has a direction, past to future, always forward, never backward. What about entropy? Because entropy is the one thing that seems to rescue time from total collapse. Entropy is the thing that gives the universe an arrow, a direction, a flow. It is the reason the past looks different from the future. The reason you can remember yesterday but not tomorrow. The reason a shattered glass does not reassemble itself. The reason smoke spreads out and never condenses back into a cigarette. Entropy, the measure of disorder in a system, always increases. That is the second law of thermodynamics. It is one of the most ironclad rules in all of physics. And it is the only law that picks out a direction in time. Every other law works the same forward or backward. You can run the equations in reverse and they still make sense, but entropy does not reverse. Entropy only goes up. And that asymmetry, that one-way street, is what most physicists point to when you ask them why time has an arrow. Entropy is the arrow. Entropy is what makes the future different from the past. Entropy is what makes time real. Except it does not. Entropy does not make time real. Entropy is not a fundamental feature of the universe. Entropy is a statistical property, a description of large numbers of particles, and the arrow it creates, the direction from past to future, is not built into the laws of physics. It is built into the initial conditions of the universe, into the fact that the universe started in a very low entropy state and has been evolving toward higher entropy ever since. And if you ask why the universe started that way, why the Big Bang was such an orderly low entropy event, the answer is that nobody knows. Physicists call it the past hypothesis. The assumption, never explained, that the universe began in a state of extremely low entropy, and from that assumption, everything else follows. The arrow of time, the asymmetry between past and future, the fact that we remember one direction and not the other, all of it is a consequence of the initial conditions, not the laws. Change the initial conditions and the arrow flips, or disappears, or never existed in the first place. Here is how entropy works. Take a box filled with gas. The gas is made of molecules bouncing around, colliding with each other, spreading out to fill the box. At any given moment, you could describe the exact state of the gas by listing the position and velocity of every molecule. That would be a complete description, a microstate. But there are an enormous number of microstates that all look basically the same from the outside. If you just measure the temperature and pressure and density, you cannot tell which microstate the gas is in. All you can say is that the gas is in some microstate consistent with those measurements. The number of microstates corresponding to a given macrostate, the measurable properties you can observe, is what entropy measures. High entropy means there are a lot of possible microstates. Low entropy means there are only a few. Now imagine you start with all the gas molecules squeezed into one corner of the box. That is a low entropy state. There are very few ways to arrange the molecules so that they are all in one corner. Let the molecules bounce around. They spread out. After a while, they fill the whole box. That is a high entropy state. There are many, many more ways to arrange the molecules so that they are spread out than there are ways to arrange them so that they are all clumped together. The gas does not spread out because there is a law forcing it to. The gas spreads out because there are more ways to be spread out. The system naturally evolves toward configurations that are more probable, and more probable means higher entropy. That is the second law of thermodynamics. In an isolated system, entropy increases over time, not because the molecules are obeying a rule that says go toward higher entropy, but because higher entropy states are vastly more numerous. The system explores the space of possible configurations, and most of those configurations are high entropy, so over time the system ends up in a high entropy state, not because it has to, because the odds overwhelmingly favor it. This is why eggs break but do not unbreak. Breaking an egg increases entropy. The molecules that were organized into a shell and a yolk and a white are now scattered across the floor. There are many more ways to arrange those molecules in a broken state than in an unbroken state. So once the egg breaks, the probability of the molecules spontaneously reassembling into an egg is astronomically small. Not impossible, just so unlikely that you would have to wait longer than the age of the universe to see it happen. The egg stays broken because broken is the high entropy state, and the universe, having started in a low entropy state, is climbing the entropy ladder, moving from order to disorder, from structure to chaos, from past to future. That climb is what creates the arrow of time, the asymmetry between past and future. If you watch a movie of an egg breaking, you can tell immediately which direction time is flowing. The egg breaks, the yolk spills, entropy increases. If you run the movie backward, you see the yolk gather itself, the shell reassemble, the egg hop back onto the counter. That looks wrong. Not because the laws of physics forbid it. The laws of physics, at the level of individual particles, are time-symmetric. They work the same forward or backward. What makes the backward movie look wrong is entropy. The backward movie shows entropy decreasing, and that almost never happens. Not because it is impossible, because it is wildly improbable. So the arrow of time, the thing that makes the future different from the past, is not a law. It is a statistical regularity, a consequence of the fact that the universe started in a low entropy state and is moving toward higher entropy, and the direction of that movement is what we call forward in time. We do not remember the future because memory is a physical process that leaves a record, and records accumulate in the direction of increasing entropy. We do not see causes follow effects because causation is tied to entropy flow. The cause is the low entropy state. The effect is the higher entropy state that follows. The arrow of time is the arrow of entropy, and the arrow of entropy is not fundamental. It is emergent, it is statistical, it is a feature of large systems starting from special initial conditions, not a feature of the laws governing those systems. And here is where things get strange. Because if the arrow of time is just a consequence of entropy, and if entropy is just a statistical property of large systems, then the arrow is not fundamental. It is not baked into the fabric of reality. It is something that emerges when you have a lot of particles and a particular kind of starting point. Change the starting point, and the arrow changes or disappears. The universe does not have to have an arrow, it just happens to have one because it started in a low entropy state, and nobody knows why. This is the past hypothesis, the assumption that the universe began in a state of extremely low entropy. The Big Bang, according to this picture, was not just hot and dense, it was ordered, smooth, homogeneous, the energy was spread out evenly, the fluctuations were tiny. It was a state with very low entropy compared to what the universe looks like now. And from that low entropy starting point, the universe has been evolving toward higher entropy ever since. Stars form, stars burn, stars die, black holes form. Black holes evaporate. Eventually, in the far future, the universe will reach a state of maximum entropy. Everything will be spread out. Everything will be the same temperature, no gradients, no structure, no complexity, no life, just a uniform, featureless, high-entropy equilibrium. Physicists call it the heat death of the universe, the point where entropy stops increasing because there is nowhere left for it to go. The point where the arrow of time, having run out of room, stops, but the arrow only exists because of the starting point. If the universe had started in a high-entropy state, if the Big Bang had been disordered and chaotic and spread out, there would be no arrow. Entropy would already be at maximum. Nothing would change. Time would not have a direction. Or more precisely, there would be no physical process that picked out a direction. You could still define a time coordinate. You could still describe the universe as existing across a four-dimensional spacetime. But there would be no asymmetry, no difference between past and future. No reason to say one direction is forward and the other is backward. The universe would just be static, timeless, a frozen block with no arrow carved into it. And that raises the question, why did the universe start in a low entropy state? Why was the Big Bang so orderly? The answer is that nobody knows. There is no law of physics that requires the universe to start that way. In fact, the opposite is true. High-entropy states are vastly more probable than low-entropy states. If you were to pick a random configuration of the universe, you would almost certainly pick a high-entropy one. The fact that the universe started in a low-entropy state is, statistically speaking, bizarre, astronomically unlikely, and yet it happened. And from that unlikely starting point, everything else followed. Stars, galaxies, planets, life, consciousness, the sensation of time passing. All of it is a consequence of the universe starting in the wrong state, the improbable state, the special state. Some physicists have tried to explain the past hypothesis. Some have proposed that the Big Bang was not the beginning, that the universe existed before the Big Bang in some other form, and the Big Bang was a transition, a bounce, a phase change, that maybe the low entropy state was set up by whatever came before. But that just pushes the question back. Why was the state before the Big Bang low entropy? Where did that order come from? Other physicists have proposed that there are many universes, a multiverse, and most of them start in high-entropy states and are boring and lifeless and timeless. We happen to live in one of the rare low-entropy universes because only those universes can support the kind of complexity needed for observers to exist. This is an application of the anthropic principle, the idea that the universe looks the way it does because if it looked any other way we would not be here to observe it. That explanation is unsatisfying to a lot of people. It feels like giving up, like saying the universe is this way because otherwise we would not be asking the question. But it may be the best answer we have. What matters for this discussion is that the arrow of time is not fundamental. It is conditional. It depends on the initial state. And if the initial state is not explained by the laws of physics, if it is just a given, a boundary condition, a fact we have to accept without deeper justification, then the arrow is not telling us something deep about the nature of time. It is telling us something about the history of this particular universe, about where it started and where it is going, but not about time itself. Not about whether time is real or fundamental or anything more than a coordinate we use to organize events. And here is the strangest part. In the timeless picture, in the block universe, entropy does not actually increase, not in any objective sense. The block universe is a four-dimensional object, a static structure. Every moment, from the Big Bang to the heat death, is laid out across space-time. All of it exists simultaneously. And in that picture, entropy is not a process. It is a pattern, a gradient across the time dimension. Low entropy at one end, high entropy at the other, but the gradient is not moving. The entropy is not climbing. It is just there, spread out across space-time like a landscape. You, moving through that landscape, experiencing one moment at a time, perceive the gradient as an increase, as a flow. But the gradient itself is not flowing. It is a static feature of the structure. The arrow of time in the block universe is not an arrow, it is a direction, a way of orienting yourself within the four-dimensional object. But the object itself is not moving, it is not evolving, it is not changing, it is frozen, complete. And the sensation you have that time is passing, that entropy is increasing, is something your consciousness constructs as it samples different slices of the block, one after another, experiencing them in sequence. But the sequence is in your experience, not in the universe. The universe contains all the slices at once, and none of them are more real, more present, more now than any other. So entropy does not save time. Entropy is not the thing that makes time real. Entropy is a statistical property that happens to have a direction in this universe because of the initial conditions, and that direction creates the arrow of time we experience. But the arrow is not fundamental. It is emergent, it is contingent, it is a feature of our particular cosmic history, not a feature of time itself. And if you take the timeless picture seriously, if you accept the block universe and the Wheeler-DeWitt equation and the quantum eraser and the neuroscience of the fabricated now, then entropy is just another pattern, another static feature of a static structure. Not a process, not a flow, not a cause, just a gradient, and the gradient points in a direction we call forward. But forward is not a property of the universe. It is a property of how we navigate the universe, how we experience it, how we remember it, how we orient ourselves within the four-dimensional landscape. But the landscape itself does not have a forward. It does not have a past or a future. It just has structure, and the structure is timeless. This is where everything converges. The block universe says the past and future exist simultaneously. The Wheeler-DeWitt equation says the quantum state of the universe does not evolve. The quantum eraser says the past is not fixed until the future is measured. Your brain says the present is a half-second-old fabrication. And now entropy, the last refuge of the arrow of time, turns out to be a statistical gradient in a static structure, not a process. Not a proof that time is real, just another pattern, another feature of the landscape. And the landscape, taken as a whole, is timeless. So what are we left with? A universe that, at its most fundamental level, does not contain time. A universe where past, present, and future are labels we apply to regions of spacetime, but not properties of spacetime itself. A universe where the arrow we experience, the flow from past to future, is an emergent phenomenon, a consequence of entropy, a consequence of initial conditions, a consequence of the fact that we are observers embedded in the structure, sampling it one slice at a time, and our brains construct the sensation of flow from the gradient we happen to be navigating. But the structure itself does not flow. It does not change. It does not evolve. It simply is. A frozen four-dimensional object. A block. A timeless whole. And yet here you are, feeling time pass, experiencing the present as something immediate and real, remembering the past and anticipating the future. The contradiction is total. The universe says time is not real. Your experience says it is. And the gap between those two things is not a gap we know how to close. Philosophers have been arguing about it for decades. Physicists have been arguing about it for longer. And the silence, the reason most scientists do not talk about this loudly, is that the implications are too large, too destabilizing, too uncomfortable. Because if time is not real, then causality is not fundamental. The idea that one event causes another, that actions have consequences, that choices shape the future, all of that becomes vastly more complicated. In a timeless universe, causes and effects are just regions of space-time sitting next to each other. There is no sense in which one produces the other. They are correlated, they are connected by the structure, but the connection is not a flow, it is not a process. It is just geometry. And the feeling you have that your choices cause outcomes, that your decisions shape what happens next, is a story your brain tells you, the narrative constructed from the correlations you observe. But the correlations are already there. They are part of the structure. They are not being created by your choices. Your choices are part of the structure too. They were always there. They were always going to happen the way they happened, not because something forced them, just because that is the shape the structure has. That is what the four-dimensional object looks like when you zoom out far enough to see the whole thing. And if causality is not fundamental, then free will, the idea that you could have done otherwise, becomes nearly impossible to defend. Not because you are being controlled, not because something external is making your choices for you, but because the choice you made was always part of the structure. It was always there. It was always going to be there. The future you are moving toward is not a range of possibilities that will collapse into reality when you get there. The future is already real. It already exists. And the choice you will make tomorrow is already sitting out there in space-time, as solid and as definite as the choice you made yesterday. You have not experienced it yet, but that is a fact about your consciousness, not a fact about the universe. The universe contains all of your choices, past and future, right now. You are just not there yet. Some people find this liberating. If the future is fixed, if every choice you will make is already part of the structure, then there is no such thing as a wrong choice, no such thing as a mistake. You did what you did because that is what the structure contains. You could not have done otherwise because otherwise is not part of the structure. You are off the hook. The burden of responsibility, the weight of regret, the anxiety about the future, all of it dissolves because there was never any real choice to begin with. You are a path through space-time, a trajectory, a shape, and the shape is what it is, not good, not bad, just there. Other people find this horrifying. If every choice is fixed, if the future already exists, if you are just a passenger watching a movie that was filmed before you were born, then what is the point? Why try? Why struggle? Why care? If everything is already decided, if the outcome is already sitting out there waiting for you to experience it, then nothing you do matters because nothing you do changes anything. The future is not shaped by your actions. The future is the future, and your actions are just part of the script, not the cause, not the driver, just another line in a play that has already been written. Both reactions miss the point. The block universe does not say your actions do not matter. It says your actions are part of what the universe is. You are not separate from the structure. You are not outside it, looking in, trying to change it. You are inside it. You are part of it. Your choices, your struggles, your regrets, your hopes, all of it is woven into the fabric. And the fact that the fabric is static, that it exists all at once, does not make your choices less real. It just makes them differently real. They are not processes. They are not events unfolding in time. They are features of the structure, aspects of the shape. And the shape is what it is because you are what you are. Your actions are not shaping the future. Your actions are the future. They are part of what the structure contains, and the structure would not be the same without them. This is where the philosophy gets uncomfortable. Because if you take it seriously, if you really internalize the idea that time is not real, that the block universe is the correct picture, that your life is a static shape stretched across space-time, then every notion of meaning you carry around has to be rebuilt from the ground up. Meaning, in the usual sense, depends on time, on the idea that what you do now affects what happens later, on the idea that the future is open, that possibilities are real, that you are steering your life in real time. But the block universe says the future is not open, it is already there, and you are not steering, you are a path, and the path is already laid out. Not because someone laid it out for you, because that is what the structure contains. That is what space-time looks like when you include your life in the description. And this is where consciousness becomes the strangest piece of the puzzle. Because everything we have talked about, the block universe, the Wheeler-DeWitt equation, the quantum eraser, the neuroscience of the fabricated now, all of it points to a universe that is static, timeless, frozen, a four-dimensional object that exists all at once and does not change, and yet you, a small piece of that object, experience it as changing. You experience time passing. You experience the present as something moving forward. You experience the sensation of now. And that sensation, according to everything we know, is a fabrication, a construct, a story your brain tells you. But it is also the only crack in the system. The only place where the static structure seems to come alive, where the frozen block seems to move, where the timeless universe seems to have a heartbeat. Consciousness is not creating time, consciousness is not making the universe flow, but consciousness is experiencing flow. And that experience, that private, subjective, fabricated sensation that you are living through moments in sequence, is the only place in the known universe where time appears to exist. Not in the equations, not in the structure, not in the external world, but in you, in the way your brain processes information, in the way your memory works, in the way you navigate the block. And the fact that the experience is a fabrication does not make it less important, it makes it more important, because it means that the sensation of time, the feeling that the universe is alive, that things are happening, that the present is real, all of that exists only in consciousness, nowhere else. The universe is dead, the structure is frozen, the block is timeless. And yet here you are, a piece of that block, experiencing it as if it were moving, making a dead cosmos believe, for a brief moment, that it is alive. This is not a comfortable place to end. It is not a resolution. It is not an answer. It is a recognition that the question is harder than anyone thought, that the universe at its foundation may not contain the thing we thought was most obvious. The thing we thought was most undeniable. The flow of time and the feeling we have, the sensation that drives every moment of our lives, may be the only place that flow exists. Not in reality, but in us. In the way we experience reality, in the crack between the static structure and the conscious observer navigating it. And that crack, that gap, that sliver of fabricated now, may be the only place in the entire universe where time is real, not because time is fundamental, but because we are experiencing it. And the experience, even if it is a lie, even if it is a story, even if it is a construct, is the only thing that makes the timeless universe feel like anything at all. So the silence makes sense now. Physicists do not talk about this because once you say it out loud, once you admit that time may not be real, that the flow is a fabrication, that the block universe is the best picture we have, you are left standing in a universe that is profoundly alien. A universe where every moment exists simultaneously, where the past is not behind you and the future is not ahead of you but beside you, parallel to you, part of the same frozen structure you are embedded in. A universe where your life is not a journey but a shape, not a process but a pattern, not a story unfolding in time but a static object stretched across space-time. experienced one slice at a time by a consciousness that constructs the sensation of flow, because that is the only way a biological organism can make sense of a reality that, at its core, does not flow at all. And the entropy, the arrow, the direction from past to future, is not proof that time is real. It is proof that the structure has a gradient, that the universe started in a special state and is moving, or appears to move, toward a different state. But the movement is in your experience, not in the structure. The structure is complete, the gradient is already there, and you, navigating that gradient, experiencing it one moment at a time, feel the flow. But the flow is not flowing, it is a static pattern, and you are the only thing in the universe that experiences it as anything other than that. So here is what we are left with: a universe that does not tick. A cosmos where the equations describing everything, when taken to their logical conclusion, contain no variable for time, where past, present, and future are coordinates on a map, not moments passing in sequence. Where the sensation you have right now, the feeling that this instant is somehow special, somehow more real than any other, is something your brain manufactures from half-second-old data, because that is the only way a conscious organism can navigate a four-dimensional block that does not care which direction you call forward. The silence among physicists is not conspiracy, it is caution. It is the recognition that some truths, once spoken, unravel everything downstream. If time is not fundamental, then causality becomes geometry, free will becomes topology, meaning becomes something you have to construct from scratch in a universe that was never built to contain it. And most people are not ready for that conversation. Most people need to believe the future is open, that choices matter, that the timeline is real, that yesterday is gone and tomorrow has not arrived, and this moment right now is the only moment that exists. But the equations do not care what you need, and they keep saying the same thing. Time is emergent, time is relational, time is a story, and the story, however convincing, however seamless, is not the thing itself. You are not moving through time. You are a shape in space-time. A static pattern stretched across dimensions you cannot